On the surface of Venus, you have 20 minutes. The air is not air. It is carbon dioxide so dense it behaves like an ocean. The pressure is equivalent to being 900 meters underwater. The temperature will melt lead, and the Soviet Union sent 10 spacecraft there. Every single one was destroyed within hours. On Mercury, you have 15 minutes before the sun rises and the radiation ends you. On Jupiter, you have 3 minutes of freefall through storms larger than Earth before the winds tear you apart. On Neptune, you have 2 minutes. The fastest winds in the solar system, 1,300 miles per hour, 5 times the speed of sound. Every planet in the solar system will end you, most of them in minutes. But on one moon of Saturn, the gravity is so low and the atmosphere is so thick that you could strap wings to your arms and fly. And on a moon of Jupiter, hidden beneath miles of ice, there is an ocean twice the volume of all Earth's oceans combined. An ocean that might not be empty. Tonight we are visiting every world, how they end you, what they are hiding, and how humanity plans to colonize them anyway. If you enjoy our nighttime science journeys, remember to like and subscribe. We highly encourage our community to discuss the video topics in the comments and react to other comments. It is the most fun when we share our thoughts. Now, let us begin. Tonight we are going on a journey that no human being has ever survived. Not to one world, to all of them. Every planet in our solar system, every major moon, every scorching hellscape and frozen wasteland orbiting our sun. And we are going to answer one question. How long would you actually last? We are not talking about vague estimates or hand-waving. We are talking about what happens to a human body, second by second, organ by organ, when it steps onto the surface of another world. We are talking about the exact temperature at which your suit fails, the exact pressure at which your chest collapses, the exact moment when the radiation turns your cells against themselves. And then, once we have survived all of that, or rather, once we have not survived any of it, we are going to ask a different question, a bigger one. How do we actually colonize these places? How does humanity leave this one fragile planet and build civilizations among the stars? We will walk on a world where the rain is made of sulfuric acid and the air is so thick it behaves like an ocean. We will stand on a moon where a hidden sea twice the volume of all Earth's oceans churns beneath miles of ice. We will visit a place where you could strap wings to your arms and fly through an orange sky, and we will discover that the deadliest planet in the solar system might also be the best place to build a floating city. But we are not starting at the beginning. We are not starting with the planet closest to the sun or the one we know best. We are starting with the one that will end you the fastest. The one the Soviet Union sent 10 spacecraft to and watched every single one of them get destroyed within hours. The one that scientists now believe may have once looked exactly like Earth, and might still have something alive in its clouds. We are starting with Venus. Chapter 1. Welcome to Venus, the fastest way to end in the solar system. You appear on the surface. There is no warning, no countdown, no gentle acclamation. One moment you are nowhere, the next you are standing on the ground of another world. And in the first fraction of a second before your brain has time to process a single sensation, every system in your body begins to fail. The air around you is not air. It is carbon dioxide so dense and so compressed that it exists in a state physicists call supercritical. That means it is neither a gas nor a liquid. It is something in between. Something that does not exist anywhere on Earth outside of specialized laboratory chambers. Something that no known form of life can survive in. The atmospheric pressure at your feet is 92 times what you would feel standing at sea level on Earth. That is the equivalent of being 900 meters underwater, roughly 3,000 feet beneath the surface of the ocean. The deepest any human has ever gone in a pressurized dive suit is about 700 meters. You are beyond that limit the instant you arrive. Your ribcage cannot expand, your lungs cannot inflate. The pressure pushes inward on every square inch of your body, with a force of roughly 1,350 pounds per square inch. That is more than the weight of a small car pressing down on an area the size of your thumbnail. Without protection, your body does not slowly compress. It collapses, the air is driven from your lungs. Your cardiovascular system fails. Consciousness ends in seconds, not minutes, seconds. But let us give you a chance. Let us put you in the most advanced spacesuit humanity has ever built. Titanium plates on the exterior, a silicon carbide outer layer rated to withstand 500 degrees, a tantalum gold anti-corrosion coating to resist the sulfuric acid in the atmosphere, internal evaporative cooling systems, oxygen recyclers, radiation shielding. Every piece of engineering ingenuity our species has ever produced, compressed into a single suit of armor. Now, how long do you last? About 20 minutes. Here is why. The surface temperature on Venus is 475 degrees Celsius. That is roughly 890 degrees Fahrenheit. For context, your kitchen oven maxes out at about 260 degrees Celsius. Lead melts at 327 degrees. Tin melts at 232. Zinc melts at 420. Venus is hotter than all of them. The surface of Venus will melt lead, tin, and zinc into puddles. And it is hotter than Mercury, the planet closest to the Sun. In fact, Venus is the hottest planet in the entire solar system, despite being nearly twice as far from the Sun as Mercury is. The reason is the atmosphere. Venus has the most extreme greenhouse effect of any planet we have ever studied. The thick blanket of carbon dioxide traps heat so efficiently that the surface temperature barely changes between day and night. It barely changes between the equator and the poles. The entire planet is a pressure cooker, and you are inside it. Your suit's cooling system fights valiantly. The evaporative systems work. For a while, but the heat is relentless. It presses in from every direction. The exterior panels begin to warp. The silicon carbide layer holds, but the thermal gradient between the outside surface and your body is so extreme that the cooling system simply cannot keep up. Within 10 minutes, your core body temperature begins to rise. Within 15 minutes, you are experiencing severe heat stroke. Your brain swells, your organs begin to shut down. By the 18th minute, your cooling system fails entirely. The suit begins to deform under the combined assault of heat, acid, and pressure. By the 20th minute, the structural integrity of the suit is compromised. The supercritical atmosphere floods in. And then there is the acid. The upper atmosphere of Venus is filled with clouds of sulfuric acid. These clouds extend from about 45 kilometers above the surface to roughly 70 kilometers up. Winds in this layer reach 360 kilometers per hour. Lightning discharges crack through the toxic haze, and the sky above you is not blue. It is a perpetual dim yellowish-orange twilight. The atmosphere is so thick that sunlight barely reaches the surface. If you looked up, you would see a smeared glow like a sunset that never ends and never brightens. The landscape around you exists in a permanent, murky gloom. We know what this surface looks like because the Soviet Union showed us. Between 1961 and 1984, the Soviet space program launched over 30 missions to Venus as part of the Venera and Vega programs. 10 spacecraft successfully landed on the surface. Every single one was destroyed. The longest any of them survived was 127 minutes. That was Venera 13, which touched down on March 1, 1982. In those 2 hours and 7 minutes, Venera 13 accomplished something extraordinary. It transmitted the first color photographs from the surface of another planet. It recorded the first sound ever captured from another world, a faint rush of wind. a mechanical click as the lens cap ejected, and then silence, punctuated by the grinding of an alien atmosphere against Soviet steel. The images Venera 13 sent back are haunting. Flat slabs of volcanic rock stretch to the horizon beneath that orange sky. The camera lens cap sits on the ground in the foreground of one image. A small piece of Earth resting on the surface of another world. Within 2 hours, the lander was gone, dissolved, crushed, cooked, reduced to scrap by the most hostile surface environment in the solar system. And here is something most people do not know. One of the Soviet Venus landers never made it to Venus at all. Cosmos 482 launched in 1972, but its upper rocket stage failed and it got stuck in Earth orbit. For 53 years, this Venus lander circled our planet. A spacecraft built to withstand the most extreme conditions in the solar system, trapped in a slow, decaying orbit around the world it launched from. In May of 2025, Cosmos 482 finally re-entered Earth's atmosphere. And because it had been engineered to survive Venus, parts of it almost certainly survived the re-entry. A machine built for another world, tougher than anything around it, falling back to Earth after half a century of waiting. Today at NASA Glenn Research Center, engineers operate something called the GEAR facility, the Glenn Extreme Environments Rig. It is a chamber that recreates the surface conditions of Venus, the heat, the pressure, the acid, and inside this chamber, researchers have tested electronics that survived 21 days under Venus surface conditions. That is a massive leap from the 2 hours Venera 13 managed, 21 days. It suggests that long-duration surface missions on Venus are not impossible. They are just extraordinarily difficult. And the missions are coming. The European Space Agency is developing Envision, an orbiter designed to map the surface of Venus in high resolution. NASA has Da Vinci and Veritas in the pipeline, though both have faced budget delays. And Rocket Lab, in partnership with MIT, is working on the Morning Star missions, potentially launching as soon as 2026. Because here is the twist. Venus, this world that destroys everything we send to its surface, may have once been the most Earth-like planet in the solar system. Evidence from past missions suggests the presence of granite, like rocks on the surface, rocks that on Earth only form in the presence of liquid water. Climate models published in recent years suggest that Venus may have had oceans on its surface for as long as 2 to 3 billion years. Temperatures were mild, conditions were habitable. Venus may have been a blue world, a living world, a world very much like ours. And then something went wrong. The greenhouse effect ran away. The oceans evaporated. The carbon locked in the rocks was released into the atmosphere, and Venus became what it is today, a warning, a mirror held up to every planet that plays too carelessly with its atmosphere. But the story does not end there, because at 50 kilometers above the surface of Venus, something remarkable happens. The temperature drops to between 30 and 70 degrees Celsius. The atmospheric pressure falls to roughly Earth sea level. The gravity is nearly identical to what you feel right now. And if you filled a balloon with a mix of nitrogen and oxygen, the same air you are breathing at this moment, that balloon would float in the thick carbon dioxide atmosphere of Venus. It would float naturally, effortlessly, like a helium balloon on Earth. In other words, a habitat filled with breathable air is a natural airship on Venus. Scientists in 2025 published research showing that the ultraviolet absorption patterns in Venus' upper atmosphere resemble those of certain organic compounds. Chemical disequilibria have been detected in the cloud layer. Iron and magnesium sulfates have been found. And the phosphine controversy, the 2020 detection of a gas associated with biological processes on Earth, remains unresolved. Something is happening in those clouds that standard chemistry does not fully explain. Venus is the most hostile surface in the solar system. It will end you in 20 minutes, even in the best suit ever made. And yet it might be hiding life in its clouds and a lost ocean in its past. We will return to Venus later in our journey, because the plan to colonize this planet is one of the most audacious ideas in the history of engineering. But first, we leave Venus behind and travel inward, toward the Sun, to the smallest planet, the one with no atmosphere and no protection from the most dangerous force in the solar system, radiation. Mercury is next, and the Sun is waiting. Chapter 2. Mercury. Where the Sun ends you in 15 minutes. Mercury is a world of extremes so violent that the planet itself seems unable to make up its mind. One side is burning, the other side is frozen, and neither side has any interest in keeping you alive. Let us start on the dark side. You arrive on the night hemisphere of Mercury, and for a moment, things seem almost manageable. The temperature is negative 173 degrees Celsius. That is brutally cold. Colder than anywhere on Earth. Colder than the deepest Antarctic winter. But your suit can handle it. Modern thermal protection is designed for exactly this kind of cold. The landscape around you looks eerily familiar. Craters, grey dust, rocky outcrops casting long black shadows. It could be the moon. It could be any airless body in the inner solar system. There is no atmosphere here, not in any meaningful sense. Mercury has what scientists call an exosphere, a scattering of atoms so thin that they barely qualify as being there at all. Sodium, hydrogen, helium, oxygen, potassium, trace amounts, functionally nothing. You take a step, the gravity is 38% of Earth's. You feel light, springy. Your footprints press into the grey regolith. The sun is nowhere to be seen. It is below the horizon. The stars above you are sharp and unblinking because there is no atmosphere to scatter their light. And for a few minutes, you might think you could survive here. You cannot. Even on the dark side of Mercury, the radiation is already working on you. Without an atmosphere or a magnetic field strong enough to deflect it, you are exposed to the full fury of the solar wind. Charged particles from the sun stream past Mercury at hundreds of kilometers per second. Galactic cosmic rays, high-energy particles from exploding stars far beyond our solar system, pass through your suit and through your body, like invisible bullets shredding your DNA as they go. Space radiation comes in 3 forms, and each one is a different kind of threat. There are galactic cosmic rays. These are the heavy hitters. Highly energetic nuclei of atoms, stripped of their electrons, accelerated to near light speed by supernovae and other cataclysmic events across the galaxy. They can penetrate several meters of solid material. No practical amount of shielding stops them all. Then there are solar particle events. These are bursts of radiation released by the sun during solar flares and coronal mass ejections. They are less energetic than galactic cosmic rays, but they come in massive waves. A single solar particle event can deliver a lethal dose of radiation in minutes if you are unshielded. And then there is ultraviolet radiation. On Earth, the atmosphere and the ozone layer block most of it. On Mercury, there is nothing between you and the full ultraviolet output of a star that appears 3 times larger in the sky than it does from Earth. On Mercury, you are receiving all 3 simultaneously. Your suit provides some protection. The outer layers absorb ultraviolet and deflect some of the lower energy particles. But galactic cosmic rays pass through it like it is not there. And if a solar particle event occurs while you are standing on the surface, the radiation dose spikes by orders of magnitude. Your electronics fail first. The radiation seeps into circuits and disrupts the delicate pathways that control your suit's life support systems. Sensors give false readings, cooling systems glitch, oxygen regulators stutter. And then the radiation reaches you. Your cells begin to sustain damage at a rate your body cannot repair. DNA double-strand breaks accumulate faster than your repair enzymes can fix them. Nausea comes first. Then vomiting. Then confusion. Your bone marrow begins to fail. Your immune system collapses. This is acute radiation syndrome. It is not a gentle process. It is less than #0. 5 is greater than. Now let us talk about what happens when the sun comes up. Mercury rotates so slowly that a single solar day lasts 176 Earth days. That means once the sun rises, it does not set for roughly 88 Earth days. If you are on the surface when the Terminator approaches, when the line between night and day creeps toward you across the cratered landscape, you have very little time to move. Because on the day side of Mercury, the temperature rises to 427 degrees Celsius. That is hot enough to melt lead, hot enough to melt zinc, and it arrives with the pitiless efficiency of a star that has no atmosphere between it and the ground. The sun appears over the horizon, and it is enormous. 3 times the angular diameter it appears from Earth, a blinding white disk with no atmospheric filtering to soften it. If you looked directly at it, the ultraviolet and visible radiation would damage your retinas in seconds. Your suit begins absorbing heat faster than it can shed it. The same suit that was keeping you alive in the freezing darkness of the night side is now being cooked from the outside. External temperatures climb past 200 degrees, past 300, past 400. Your cooling system screams at maximum capacity, and it is not enough. Researchers at Brookhaven National Laboratory, working with NASA's Space Radiation Element, have been studying what space radiation does to the human cardiovascular system. Their findings from animal models show that radiation causes arterial stiffening, structural damage to the heart, long-term degradation of the entire circulatory system, and that is from the levels astronauts experience in low Earth orbit, which are a fraction of what you would encounter on Mercury. On Mercury's day side, you are not experiencing long-term degradation. You are experiencing catastrophic system failure. The timeline is roughly 15 minutes. Your suit cannot protect you from the combined assault of radiation and heat. The electronics fail. The cooling system shuts down. Your body temperature rises past the point where your proteins begin to denature. Your brain swells. You lose consciousness, and within 15 minutes of the sun appearing over that cratered horizon, you are gone. So Mercury is a wasteland, a dead world baking and freezing in equal measure. There is nothing here for us, right? Not exactly. NASA's Messenger spacecraft orbited Mercury from 2011 to 2015. It was the first spacecraft to orbit the planet, and it sent back data that changed our understanding of this small, dense world. Among the most intriguing discoveries were features on Mercury's surface that scientists described as having a Swiss cheese appearance, irregular depressions, collapse features, hollows. Some of them appeared to be entrances to underground cavities, possible lava tubes. On the Moon, we know that lava tubes exist. Ancient tunnels carved by flowing lava beneath the surface billions of years ago. Some of them are enormous, large enough to contain entire cities. And they provide something that the surface of an airless world cannot: shielding. A lava tube 20 meters below the surface of Mercury would be shielded from solar radiation, shielded from the extreme temperature swings, protected from micrometeorites. A lava tube on Mercury could be a habitat, not a comfortable one, not an easy one, but a possible one. Of course, there are problems. Mercury's gravity is only 38% of Earth's, the same as Mars. Long-term exposure to low gravity causes bone density loss at a rate of roughly 1 to 2% per month. Muscle atrophy, cardiovascular degeneration. Fluid redistribution in the body leads to increased intracranial pressure and a condition NASA calls SANS, spaceflight-associated neuroocular syndrome. Your eyes change shape. Your vision blurs. The longer you stay in low gravity, the worse it gets. Mercury is also incredibly difficult to reach. Counterintuitively, it takes more energy to send a spacecraft to Mercury than to send one to Pluto. You are fighting against the sun's gravity the entire way. You need to slow down enormously to enter orbit around a planet that sits deep in the Sun's gravitational well. NASA's Messenger took 6.5 years and performed 6 gravity assist maneuvers at Earth, Venus, and Mercury itself before finally settling into orbit. Mercury is not a colonization target, not in any foreseeable future. It is a radiation trap with a tantalizing secret buried underground, a world that punishes the surface and rewards the depths. A reminder that in our solar system, survival often means hiding. But we are not hiding today. We are continuing outward, past Venus, past Earth, to the planet that humanity has dreamed about visiting for over a century. The one that looks the most like home from a distance but up close has its own very specific ways of ending your story. They are just slower, more patient, more insidious. Mars is next, and it feels like home right until it does not. Chapter 3. Mars, the slow collapse that feels like home. You land at the equator during Martian summer, and for the first time on this entire journey, something feels almost right. The temperature is 20 degrees Celsius. That is a pleasant spring afternoon on Earth. The sky is not black like Mercury. It is not orange like Venus. It is a butterscotch pink, stretching from horizon to horizon, with the sun hanging pale and small above the rust-colored desert. You take a step, and you feel incredible. Mars' gravity is only 38% of Earth's, which means if you weigh 80 kilograms on Earth, you weigh about 30 kilograms here. Every step has a little bounce in it. Every movement feels effortless. Your muscles feel powerful. Your body feels light. For a brief, wonderful moment, Mars feels like a place where a human could live. That feeling is a lie. The atmosphere around you is 100 times thinner than Earth's. If you took off your helmet right now, here is what would happen. The moisture on your tongue would begin to boil. Not because it is hot, but because the atmospheric pressure is so low that the boiling point of water drops below body temperature. The saliva on your tongue, the tears in your eyes, the moisture lining your lungs, all of it would begin to vaporize. You would lose consciousness in about 15 seconds. Your body would not explode. That is science fiction. But your soft tissues would swell, gas would form in your blood, and within about 90 seconds you would be beyond recovery. The atmosphere is 95% carbon dioxide. There is some nitrogen, some argon, virtually no oxygen. You cannot breathe it. But the atmosphere is there, and it does something important. It provides just barely enough pressure to keep liquid water from existing on the surface, but it provides enough to carry dust. Martian dust. And Martian dust is not like Earth dust. In 2022, NASA released images from the Curiosity rover showing its wheels torn apart by the abrasive Martian soil. The rocks and regolith on Mars are coated in perchlorates. These are chlorine-based chemical compounds that are toxic to human biology. They disrupt thyroid function. They interfere with iodine uptake. Prolonged exposure causes metabolic damage. And unlike Earth dust, which is rounded by water erosion over millions of years, Martian dust has never been tumbled by rain or rivers. It is sharp, angular, jagged at the microscopic level. It clings to everything. It gets into every seal, every joint, every crevice of your suit. And if you inhale it, those sharp particles embed themselves in lung tissue like tiny knives coated in industrial chemicals. Then there is the radiation. Mars has no global magnetic field. It lost it billions of years ago when its core cooled and the internal dynamo that generates a magnetic field shut down. Without a magnetic field, and with an atmosphere 100 times thinner than Earth's, Mars offers almost no protection from space radiation. On the surface of Mars, you receive radiation doses roughly 20 times higher than what you would experience on the surface of Earth. And during a solar particle event, when the sun hurls a massive burst of charged particles across the solar system, that number spikes dramatically. A single major solar event could deliver a radiation dose equivalent to several years of normal exposure in just a few hours. NASA uses a framework called RIDGE to categorize the dangers of long-duration space missions. The letters stand for radiation, isolation, distance, gravity, and environment. Mars hits all five. The radiation degrades your cells. The isolation erodes your psychological stability. The distance means help is impossibly far away. Communication with Earth has a delay of 4 to 24 minutes depending on where the two planets are in their orbits. If something goes wrong, you cannot call for help and get an answer in real time. If something goes catastrophically wrong, rescue is not coming. Not in days, not in weeks, not ever. The gravity weakens your bones. And the environment, the cold, the dust, the thin atmosphere, works against you every single moment. And the cold. We should talk about the cold. That pleasant 20-degree afternoon you arrived in, it does not last. At night, temperatures on the Martian equator plummet to -70 degrees Celsius. At the poles, it drops to -150. Mars averages -60 degrees across the planet. That comfortable afternoon was a fleeting exception. The rule on Mars is bitter, relentless cold. Your body does not handle low gravity well over time. We know this from decades of research on the International Space Station. In microgravity, astronauts lose bone density at 1 to 2% per month. Their muscles atrophy. Their hearts shrink because they no longer have to pump blood against full gravity. Fluid shifts upward in the body, pooling in the head and chest. This increases intracranial pressure and leads to what NASA calls SANS, spaceflight-associated neuroocular syndrome. The back of the eye flattens, the optic nerve swells, vision becomes blurred. Some astronauts have returned from 6-month missions on the International Space Station with permanent changes to their eyesight. Mars' gravity is higher than microgravity, but still only 38% of Earth's. Nobody knows whether that is enough to prevent the worst of these effects. No human being has ever lived at 38% gravity for an extended period. We literally do not know what it does to us. The experiments have not been run because the only place to run them is Mars. So let us talk about your suit. Your spacesuit on Mars is your entire world. It provides oxygen. It maintains pressure. It regulates temperature. It shields you from some radiation, though not enough. And it gives you roughly 10 hours. That is how long a single extravehicular activity can last on Mars before your oxygen supply is depleted and your carbon dioxide scrubbers are saturated. 10 hours. Then you go back inside. In 2023, NASA began the CHAPEA mission at Johnson Space Center. 4 crew members entered a 3D printed habitat of roughly 1,700 square feet. It was designed to simulate life on Mars. They lived inside for an entire year. They grew crops. They conducted simulated surface walks. They experienced communication delays with mission control. And the most important finding? It was not the food. It was not the technology. It was the psychology. The primary limiting factor for a Mars mission is the human mind, the isolation, the confinement, the monotony, the knowledge that you are further from home than any human has ever been, and that the distance between you and everything you love is measured not in miles, but in months. Mars will not end you quickly. That is what makes it different from every other world we have visited so far. Venus gives you 20 minutes. Mercury gives you 15. Mars gives you time. Time enough to build a habitat. Time enough to grow food. Time enough to start a new life on another planet. But it also gives you time to realize how alone you are. Time to feel the dust grinding its way into every mechanism you depend on. Time to notice your bones getting lighter, your vision getting softer. Time to understand that the pleasant spring afternoon was just one face of a world that is slowly, patiently, methodically working against you in ways you cannot see and cannot stop. But Mars is where we are going. Despite everything, Despite the radiation and the cold and the dust and the isolation and the gravity and the distance, Mars is the target. It is the one planet in the solar system where humanity has concrete plans to send people. Plans that, as of February 2026, have been delayed and complicated and pushed back. But plans that still exist. We will talk about those plans in detail later. The rockets, the robots, the habitats, the timeline, the setbacks, all of it. For now, we leave Mars and its patient dangers behind, because we are done with the rocky planets. The inner solar system is behind us. What lies ahead is bigger, colder, stranger, and far more dangerous. We are heading for the gas giants, and the first one we reach, the largest planet in the solar system, is a world where the word surface has no meaning, where the storms are larger than Earth, where the magnetic field is so powerful it would fry every circuit in your body before you got close enough to see the clouds. Jupiter is next, and it is angry. Chapter 4. Jupiter, 3 minutes in the atmosphere of a god. There is a moment during your approach to Jupiter when the scale of what you are looking at overwhelms every reference point your brain has ever built. You have seen planets before on this journey. Venus with its thick orange haze, Mercury small and grey and pockmarked, Mars red and dusty and deceptively familiar. But Jupiter is something else entirely. Jupiter is not a planet the way you think of planets. It is a failed star, a ball of hydrogen and helium, so massive that it contains more matter than every other planet in the solar system combined, more than twice as much. If Jupiter had been about 80 times more massive, the pressure and temperature at its core would have been enough to ignite hydrogen fusion, and Jupiter would have become a star. Our solar system would be a binary star system. Earth might never have formed. Life as we know it might never have existed. Jupiter has a diameter of roughly 143,000 kilometers. You could fit 1,300 Earths inside it. The Great Red Spot alone, a storm that has been raging for at least 350 years, is larger than the entire planet Earth, and you are falling into this. But before you even reach the atmosphere, Jupiter is already trying to end you. The magnetic field. Jupiter possesses the most powerful magnetic field of any planet in the solar system. It is roughly 18,000 times stronger than Earth's. It extends 7 million kilometers toward the Sun and stretches back in the other direction, nearly far enough to touch Saturn's orbit. This magnetic field traps charged particles from the solar wind and from volcanic eruptions on Jupiter's moon Io, creating radiation belts of extraordinary intensity. The engineers who designed the Europa Clipper spacecraft describe Jupiter's radiation environment as the nastiest in the solar system. Every close flyby of Europa will expose the spacecraft to the equivalent of 100,000 chest X-rays. The instruments sit inside a titanium radiation vault lined with polyethylene and Kevlar. And even with that protection, the mission is designed to limit time spent inside the radiation belts because the electronics cannot withstand prolonged exposure. Your suit has nothing comparable to that vault. As you approach Jupiter, the radiation begins degrading your systems long before you touch the cloud tops. Circuit boards fail. Sensors give false readings. Communication systems crackle and die. And then you enter the atmosphere. NASA's Galileo probe did this on December 7, 1995. It was the first and so far only spacecraft to descend into the atmosphere of a gas giant. The probe entered Jupiter's atmosphere at a speed of roughly 170,000 kilometers per hour. For 2 minutes, it experienced deceleration forces of 230 times the force of gravity. 230 Gs. A fighter pilot loses consciousness at 9 Gs. At 230 Gs, every bone in your body would shatter, every organ would rupture. You would not survive the entry, let alone the descent. But the Galileo probe did. It survived the entry, it deployed a parachute, and it began to fall. For 58 minutes, it transmitted data as it descended 87 miles into the atmosphere. Temperature readings, pressure readings, wind speed measurements, composition data, and then the signal stopped. The probe was crushed, or overheated, or both. It simply ceased to exist. Let us walk through what you would experience if somehow you survived the entry. You are falling through the upper atmosphere. The first thing you encounter is ammonia. Clouds at roughly negative 100 degrees Celsius. These are the white and tan bands you see in photographs of Jupiter. They are beautiful from a distance. From inside, they are a blinding toxic fog. Below the ammonia clouds are ammonium hydrosulfide clouds. Below those are water ice clouds. The temperature is rising. The pressure is increasing. Within a minute or so of descent, you pass through a region where the atmospheric pressure is roughly equal to sea level on Earth. 1 bar. This is sometimes called the surface of Jupiter, but there is nothing solid here. There is no ground. There is just thicker and thicker and hotter gas extending downward for tens of thousands of kilometers. And then the winds hit. Jupiter has the most powerful sustained winds in the inner solar system. They blow at over 370 miles per hour in the jet streams between the cloud bands. But it is not just the speed, it is the turbulence. You are thrown into massive vortices. Shearing winds tear at you from different directions simultaneously. The G-forces from being flung through these atmospheric currents would render you unconscious and then would break you apart. Lightning bolts spanning over 600 miles crack through the clouds around you. Jupiter has some of the most powerful lightning ever recorded in the solar system. As you continue to fall, the pressure mounts. 5 bars, 10 bars, 20. The temperature climbs past the boiling point of water, past 200 degrees, past 500. Your suit is now being compressed and heated simultaneously. At some point, the hydrogen gas around you becomes so compressed that it transitions into a liquid. You are no longer falling through an atmosphere. You are sinking through an ocean of liquid hydrogen. And still, there is no bottom. Deeper still, thousands of kilometers below the cloud tops, the liquid hydrogen is compressed so intensely that it undergoes another phase change. It becomes metallic hydrogen, a state of matter that barely exists on Earth. In this state, hydrogen conducts electricity like a metal. It is this layer of metallic hydrogen circulating deep within Jupiter's interior that generates the planet's monstrous magnetic field. At the very center lies a core. Scientists believe it is made of compressed rock, metal, and exotic hydrogen phases. The pressure at Jupiter's core is estimated to be roughly 25 million times the atmospheric pressure at Earth's surface. The temperature is approximately 20,000 degrees Celsius, hotter than the surface of the Sun. Your total survival time inside Jupiter, measured from the moment you enter the cloud tops to the moment the winds or the heat or the pressure or the radiation ends you, is approximately 3 minutes, probably less. The Galileo probe lasted 58 minutes because it was an engineered sphere of titanium and beryllium designed to withstand forces that would liquefy human tissue. You are not an engineered sphere. You are a sack of water and carbon wrapped in the best suit your species can build, and Jupiter does not care. But Jupiter itself is not the most interesting part of this chapter. The planet is a gas giant. It has no surface. There is nowhere to stand. There is nothing to colonize. Jupiter is a killing field for anything that enters it. What is interesting are the things orbiting Jupiter. Jupiter has 95 known moons. 4 of them are enormous. They are called the Galilean moons because Galileo Galilei first observed them through his telescope in 1610. Their names are Io, Europa, Ganymede, and Callisto. Io is the most volcanically active body in the solar system. Its surface is constantly being reshaped by eruptions of sulfur and silicate lava, driven by the tidal forces of Jupiter's gravity, squeezing and stretching the moon's interior. Ganymede is the largest moon in the solar system, bigger than the planet Mercury, and it has its own magnetic field, the only moon known to have one. Callisto is ancient and cratered, a frozen museum of the solar system's violent early history. And then there is Europa. Europa is a moon roughly the size of Earth's moon. Its surface is ice, smooth, cracked, scarred, with lines that stretch for hundreds of kilometers. It is one of the smoothest objects in the solar system. And beneath that ice is an ocean, a global ocean of liquid salt water that contains roughly twice the volume of all the water in all the oceans on Earth combined. An ocean that has existed for billions of years. An ocean that might not be empty. We launched a spacecraft to find out. It left Earth on October 14, 2024. It is called Europa Clipper. It is the largest spacecraft NASA has ever built for a planetary mission. It will arrive at the Jupiter system in 2030. And what it finds beneath that ice could be the most important discovery in the history of science. Europa is our next destination. And it is 15 minutes you will never forget. Chapter 5. Europa. 15 minutes above an alien ocean. You are standing on the surface of Europa, and the first thing you notice is how still it is. There is no wind, there is no sound, there is no weather of any kind. Just silence so absolute that the only thing you can hear is the hiss of oxygen cycling through your helmet and the rhythm of your own breathing. Beneath your feet, the ground is ice, not the rough, dirty ice of a frozen pond or the compacted ice of a glacier. This is water ice so cold that it behaves more like rock than anything you would recognize as frozen water. The surface temperature is -150 degrees Celsius. The ice extends downward for roughly 20 to 35 kilometers beneath you. And below that ice, far below it in the permanent darkness where no sunlight has ever reached, lies an ocean. The ocean beneath Europa is one of the most remarkable discoveries in the history of planetary science. It is global. It covers the entire moon. It contains roughly twice the volume of all the water in every ocean on Earth combined. It is salt water, and it has been there for a very long time, possibly for billions of years. Billions of years of liquid water, billions of years of chemistry, billions of years for something to happen. But before we talk about what might be swimming beneath your feet, let us talk about what is happening to you right now. Because Europa sits squarely inside Jupiter's radiation belts, and those radiation belts are trying to destroy you. Jupiter bathes Europa in a constant bombardment of high-energy charged particles. The radiation dose on the surface of Europa is roughly 540 rem per day. For comparison, the annual radiation dose for the average person on Earth is about 0.3 rem. The lethal dose for a human being is roughly 400 rem delivered over a short period. On Europa, you receive a lethal dose in less than 18 hours. But that is the slow calculation. In practice, the radiation is degrading your electronics within minutes. Your suit's sensors begin giving erratic readings. Your communication systems fail. Your oxygen recycling system begins to malfunction as the radiation damages the circuits that control it. Here is the cruel irony. That same radiation that is ending you is also creating something extraordinary. When Jupiter's charged particles slam into Europa's ice surface, they split water molecules apart. Hydrogen and oxygen. The hydrogen escapes into space because Europa's gravity is too weak to hold it, but some of the oxygen stays. NASA's Juno spacecraft used its JADE instrument to make the first direct measurements of this process. Europa generates roughly 26 pounds of oxygen per second through radiation bombardment of its surface ice. An ocean world, creating breathable oxygen from its frozen shell. And you are standing on top of it, suffocating inside a radiation storm. Your survival time on Europa's surface is approximately 15 minutes, not because of the cold. Your suit handles the cold. Not because of the vacuum. Europa has the thinnest wisp of an atmosphere, essentially nothing, but your suit maintains pressure. It is the radiation. 15 minutes of exposure and your electronics are compromised. your life support begins to fail. Your cells are being damaged at a rate that makes recovery impossible. 15 minutes, and you are beyond saving. Now let us look down. In 2025, a study published in Nature Astronomy used data from the Juno spacecraft's microwave radiometer to measure the thickness of Europa's ice shell. The result was approximately 29 kilometers, plus or minus 10. That is the barrier between you and the ocean below. The study also found that fractures and pores extend hundreds of meters deep into the ice, creating potential pathways for material to move between the surface and the ocean beneath. This matters enormously, because the surface of Europa is not just ice. NASA's James Webb Space Telescope has detected crystalline water ice, sodium chloride, which is ordinary table salt, carbon dioxide, and hydrogen peroxide in regions of Europa's surface called chaos terrains. These are areas where the ice appears to have been disrupted and reformed, broken apart and refrozen. Terra Regio and Pauis Regio are two such regions. And the chemicals found there are not random. They are the basic ingredients for habitability: salt water, carbon, oxidants, the building blocks of the chemistry that life requires. In January of 2026, a study published in the Planetary Science Journal by researchers at Washington State University revealed something even more remarkable. Salt-rich ice on Europa's surface can become dense enough to sink, to drip downward through the ice shell and potentially reach the ocean beneath. The process takes roughly 30,000 years. That sounds slow by human standards, but by geological standards it is practically instantaneous. And it means that the chemicals on Europa's surface, the salt, the carbon dioxide, the oxidants created by Jupiter's radiation, have a delivery mechanism. They can reach the ocean. They can feed whatever chemistry is happening down there. And there is more. In 2025, researchers published findings suggesting that even without hydrothermal vents on the ocean floor, radioactive elements in Europa's rocky core could power microbial life through a process called radiolysis. Radioactive decay splits water molecules into hydrogen and oxygen ions, providing a source of chemical energy that life could use. On Earth, we have found ecosystems deep underground powered by exactly this kind of radioactive chemistry. Microbes living kilometers below the surface in total darkness, feeding on the energy released by the decay of uranium and thorium in surrounding rocks. The implications are staggering. Europa has an ocean. That ocean has salt. It has a source of chemical energy from below, through radioactive decay, and potentially through hydrothermal vents. It has a source of chemical ingredients from above, through the slow sinking of irradiated surface ice. It has been stable for billions of years. On Earth, life appeared almost as soon as conditions allowed it. If the same is true on Europa, then beneath that cracked frozen surface, something may be alive right now. Not might have been, not could theoretically be, may be alive right now. As you listen to these words, we sent a spacecraft to find out. Europa Clipper launched on October 14, 2024, from Kennedy Space Center on a SpaceX Falcon Heavy rocket. It performed a gravity assist flyby of Mars in February 2025 and will swing past Earth in December 2026. It will arrive at the Jupiter system in April of 2030. Once there, it will not orbit Europa directly because Jupiter's radiation belts would destroy the spacecraft too quickly. Instead, it will orbit Jupiter and dive in for close flybys of Europa, 49 of them. Each flyby will be a few minutes of intense data collection, followed by a retreat to safer distance. The spacecraft carries 9 science instruments, all housed inside a radiation vault. Radar to probe the structure of the ice shell. Spectrometers to analyze the chemical composition of the surface. A magnetometer to characterize the ocean. Cameras, thermal imagers, dust analyzers, and an ultraviolet spectrograph that will search for plumes. Because scientists suspect that Europa may be venting water vapor from its ocean through cracks in the ice, shooting geysers 120 miles into space. If those plumes exist, Europa Clipper will fly through them and taste the ocean without ever having to drill through the ice. What Europa Clipper finds could change everything. If the chemistry is right, if the ocean has the ingredients and the energy and the stability, then life beyond Earth is not a theoretical possibility. It is a neighbor, swimming in the dark beneath a frozen shell around a moon of the largest planet in our solar system. But Europa is not the only moon with secrets. Saturn has one that is even stranger. A moon with a thick atmosphere. A moon where it rains. A moon where rivers flow into lakes and seas. Not water, methane. A moon where the gravity is so low and the air is so thick that a human with wings strapped to their arms could fly. And on this moon, scientists have just discovered something that no one expected. The building blocks of cells forming naturally in alien lakes. We are going to Saturn and to Titan. Chapter 6. Saturn and Titan. 5 minutes of falling, then a world where you could fly. Saturn is the most beautiful planet in the solar system, and it wants nothing to do with you. From a distance, it is breathtaking. The rings stretch outward for nearly 300,000 kilometers from the planet's center. They are made of billions of individual pieces of ice and rock, ranging in size from grains of sand to chunks as large as houses. The rings are astonishingly thin. If you could shrink Saturn to the size of a football field, the rings would be thinner than a sheet of paper. They are a cosmic illusion, a structure so vast and so flat that it seems impossible. Below the rings, the planet itself is a gas giant, second only to Jupiter in size. Saturn is roughly 9.5 times the diameter of Earth. It is composed almost entirely of hydrogen and helium. And like Jupiter, there is no surface, there is no ground. There is only atmosphere getting denser and hotter the deeper you go, until the gas becomes liquid and the liquid becomes something else entirely. You begin your descent into Saturn's upper atmosphere. The first thing you see is an aurora. Saturn has a magnetic field, and like Earth, that magnetic field interacts with the solar wind to produce shimmering lights near the poles. But Saturn's aurora is powered by different mechanisms than Earth's. Some of it comes from the interaction between Saturn and its moon Enceladus, which sprays water ice from its south pole directly into Saturn's magnetic field. Below the aurora, you enter the troposphere. This is where Saturn keeps its weather. And Saturn's weather is violent. Hurricanes with winds reaching over 400 meters per second. That is roughly 1,300 feet per second, many times stronger than any storm ever recorded on Earth. The strongest hurricane winds on Earth reach about 90 meters per second. Saturn quadruples that. Dense clouds of ammonia crystals give Saturn its characteristic yellow appearance. The clouds wrap around the planet in bands, driven by jet streams that circle the equator at speeds exceeding 500 meters per second. You are falling through this. The temperature drops below -200 degrees Celsius. Ice forms on your suit, your visor frosts. The winds hurl you sideways at speeds your suit was never designed to withstand. The turbulence is violent enough to cause physical trauma, even inside your pressurized armor. And the deeper you fall, the worse it gets. Pressure mounts. Temperature eventually begins to rise as compression heats the deepening atmosphere. Your electronics fail in the cold. Your suit deforms under the pressure. Total survival time inside Saturn's atmosphere, roughly 5 minutes, probably less. You are conscious for perhaps 3 of those minutes, and then the gas giant swallows you without a trace. But Saturn is not the destination. Saturn is the doorway, because orbiting this ringed gas giant is a collection of 83 known moons, and one of them is the most Earth-like world in the outer solar system. Its name is Titan, and everything about it will surprise you. Titan is the second largest moon in the solar system. Only Jupiter's Ganymede is bigger. Titan is larger than the planet Mercury, and it is the only moon in the entire solar system that has a dense atmosphere. Not a thin wisp, not a trace exosphere, a real atmosphere, thick enough that the surface pressure on Titan is 1.5 times the atmospheric pressure at sea level on Earth. You would feel it. If you stood on Titan without a suit, the pressure on your body would be slightly higher than what you feel right now. That atmosphere is primarily nitrogen, just like Earth's. Roughly 98% nitrogen with small amounts of methane and hydrogen. There is no oxygen. You cannot breathe it. But here is the extraordinary thing. You would not need a pressure suit. On Titan, the atmospheric pressure is so close to Earth's that a simple insulated suit with a respirator would keep you alive. No rigid helmet, no pressurized joints, warm clothing and an oxygen mask. That is all that stands between you and one of the most alien landscapes in the solar system. The temperature is the problem. -180 degrees Celsius. That is staggeringly cold. Cold enough to turn methane into a liquid. Cold enough to make water ice as hard as granite. Your thermal protection systems are working constantly to keep your body warm against the frigid atmosphere pressing in on every side. Titan's thick atmosphere actually makes the cold more dangerous than on airless worlds, because the dense air conducts heat away from your suit far more efficiently than vacuum. On the moon, you lose heat only through radiation, which is slow. On Titan, you lose it through conduction and convection, which is fast. Your survival time on Titan's surface is roughly 2.5 hours before your thermal systems are overwhelmed and your body temperature begins to drop. But in those 2.5 hours, you would experience something no human has ever experienced: a world with weather. It rains on Titan, not water, methane. Liquid methane falls from orange clouds in a hazy golden sky. It collects in rivers that carve channels through water ice bedrock. It flows into lakes and seas. Kraken Mare, the largest sea on Titan, is bigger than the Caspian Sea on Earth. Ligeia Mare and Punga Mare are smaller but still enormous by any standard. Titan has more liquid on its surface than any world in the solar system besides Earth. Hundreds of times more liquid hydrocarbons than all of Earth's known oil and natural gas reserves combined. The gravity on Titan is 14% of Earth's, roughly the same as our moon. You weigh almost nothing, and combined with the thick atmosphere, this creates a possibility that exists nowhere else in the solar system. You could fly. Not in an aeroplane, not in a helicopter. You, personally, with wings strapped to your arms. The low gravity means you need very little lift to stay airborne. The thick atmosphere means your wings have plenty of air to push against. A human being on Titan could achieve powered flight using nothing but muscle strength and a set of lightweight wings. You could soar over methane lakes beneath an orange sky with the pale rings of Saturn arcing overhead through the haze. It is one of the most extraordinary possibilities in all of planetary science. And now we come to the discovery that changed everything. In 2025, NASA published research conducted by Christian Mayer and NASA scientist Connor Nixon describing how simple molecules in Titan's methane lakes could naturally form structures called vesicles. These are tiny bubble-like compartments enclosed by a double layer of molecules. On Earth, vesicles are the precursors to living cells. They are the structures that allow chemistry to become biology by creating an inside and an outside. A boundary, a container, the first step toward a living cell. On Titan, the mechanism works differently than on Earth. When methane rain falls into a hydrocarbon lake, it creates a spray of tiny droplets. These droplets get coated by amphiphilic molecules, molecules with one end that interacts with the liquid methane and one end that avoids it. When a coated droplet falls back into the lake, it picks up a second layer of these molecules, forming a bilayer membrane. A vesicle, a tiny hollow sphere of organized chemistry, floating in an alien sea. Over time, the most stable vesicles would persist while less stable ones would break apart. This is natural selection at the chemical level, competition and survival among structures that are not alive, but that are taking the first steps toward the organization that life requires. The researchers propose that this process could lead to the formation of primitive protocells, not life, not yet, but the architecture that life needs to begin. In the same year, a study from Chalmers University and NASA published in the Proceedings of the National Academy of Sciences found that hydrogen cyanide can form stable crystals with methane and ethane under Titan-like conditions. This breaks a fundamental rule of chemistry called like dissolves like. Hydrogen cyanide is a molecule critical to the formation of amino acids and nucleobases, the building blocks of DNA and proteins. The fact that it can integrate into Titan's hydrocarbon chemistry means that the raw materials for life's most essential molecules are available in Titan's environment. NASA's Dragonfly mission is a rotorcraft that will fly through Titan's atmosphere, landing at multiple sites to study the Moon's surface composition and chemistry. It will not visit the lakes directly, but it will provide ground truth data about the chemical environment that makes this alien chemistry possible. Titan is a world where methane rain falls from an orange sky, where rivers of liquid hydrocarbons carve valleys through ice as hard as stone, where seas larger than any lake on Earth lap against frozen shores, where a human could fly, and where the building blocks of life may be assembling themselves in alien lakes right now. But we are not done with the outer solar system. There are two more giants waiting in the cold. Worlds so distant that the sun is barely more than a bright star. Worlds with the fastest winds and the coldest temperatures of any planet we have visited. The ice giants are next, and they are the loneliest places in the solar system. Chapter 7. The Ice Giants. Uranus, Neptune, and the coldest endings. We have now reached the part of the solar system where the sun is a memory. It is still there. You can see it, a bright point of light, brighter than any star, but no longer a disk, no longer a source of warmth. Out here beyond Saturn, the sun provides so little heat that the temperature difference between facing it and facing away from it is almost meaningless. You are cold. Everything is cold, and it is only going to get colder. Uranus is the seventh planet from the sun. It orbits at an average distance of roughly 2.9 billion kilometers. Sunlight takes 2 hours and 40 minutes to reach it. And there is something immediately wrong with Uranus. Something that sets it apart from every other planet in the solar system. It is tipped over. Uranus' axial tilt is 98 degrees. That means instead of spinning upright, like most planets, or at a modest angle like Earth, Uranus essentially rolls around the sun on its side. Its poles take turns pointing almost directly at the sun. This creates the most extreme seasonal variation of any planet. When the South Pole faces the sun, it receives continuous sunlight for roughly 42 Earth years. Then the planet rolls, and the North Pole takes its turn. The equator experiences something like a normal day-night cycle only during brief transitional periods. Nobody knows exactly why Uranus is tilted this way. The leading theory is that a massive collision with an Earth-sized object early in the solar system's history knocked it sideways. You enter the atmosphere, and immediately the wind hits. 560 miles per hour. Uranus winds are not the fastest in the solar system, but they are punishing. The atmosphere is hydrogen and helium with traces of methane. It is the methane that gives Uranus its distinctive blue-green color. Methane absorbs red light from the sun's feeble rays and reflects blue and green. The temperature is negative 220 degrees Celsius. Your suit was designed for extreme cold, but this exceeds its capacity within minutes. The thermal systems struggle. The insulation is overwhelmed by the dense, frigid atmosphere pressing in from all sides. Internal temperatures begin to drop. Your extremities go numb. The fluid in your joints begins to thicken. Your reactions slow, and you are falling. There is no surface. Like Jupiter and Saturn, Uranus has no ground to land on. Only atmosphere getting denser and stranger the deeper you go. At some point, the hydrogen transitions to a hot, dense fluid. deeper still, scientists believe there may be a slurry of water, ammonia, and methane compressed to exotic states under enormous pressure. Some researchers have speculated that deep within Uranus and Neptune, the pressure and temperature are right to compress carbon atoms into diamonds. It may literally rain diamonds in the interiors of the ice giants. Your survival time inside Uranus is 3 to 5 minutes. The cold takes you first. Your suit cannot maintain livable temperatures against the relentless conduction of that dense, frigid atmosphere. You lose consciousness as your core temperature drops below 30 degrees Celsius. Your heart rhythm becomes erratic, ventricular fibrillation, and then silence. Uranus has 27 known moons. The largest is Titania, about half the size of Earth's moon. On Titania, you would weigh roughly 4.5 pounds. The second largest is Oberon, then Umbriel, Ariel, and Miranda. Miranda is one of the strangest objects in the solar system. It appears to have been shattered and reassembled. Its surface is a chaotic patchwork of different terrain types. Canyons, cliffs, ridges, and plains jumbled together as if the moon was broken apart by a catastrophic impact and the pieces fell back together in the wrong order. On Miranda, you would weigh just over 2 pounds. Move too quickly, and you would drift off the surface entirely. Neptune is the last planet, the 8th and most distant world in our solar system since Pluto was reclassified. It orbits at an average distance of roughly 4.5 billion kilometers from the Sun. Sunlight takes over 4 hours to reach it, and Neptune has one distinction that no other planet can claim. It has the fastest winds in the solar system, 1,300 miles per hour, 5 times the speed of sound. When NASA's Voyager 2 spacecraft flew past Neptune in August of 1989, it measured wind speeds that defied explanation. Neptune receives very little energy from the Sun. It should be a quiet, frozen world. Instead, it is one of the most dynamic. Its atmosphere rages with storms and jet streams that move at speeds no other planet can match. The Great Dark Spot observed by Voyager 2 was an anticyclonic storm, the size of Earth, with winds screaming around its edges at over 2,300 kilometers per hour. You would not survive 2 minutes inside Neptune's atmosphere. The winds alone would tear your suit apart. The temperature is below negative 200 degrees Celsius. The atmosphere is hydrogen, helium, and methane. The radiation at Neptune is lower than at Jupiter, but it is irrelevant because the cold and the wind end you long before radiation becomes a factor. Neptune has 14 known moons. The largest is Triton, and Triton is strange. It orbits Neptune backwards, retrograde, in the opposite direction to Neptune's rotation. This means Triton was almost certainly not born alongside Neptune. It was captured, pulled from its original orbit by Neptune's gravity, and trapped in a slow retrograde spiral. Triton has active geysers that shoot nitrogen gas and dark particles 8 kilometers into the sky. It has a surface of frozen nitrogen with pinkish deposits of organic compounds, and it has a thin atmosphere of nitrogen and methane. Voyager 2 is still the only spacecraft to have visited Neptune. It flew past in 1989 and sent back the images that revealed the Great Dark Spot, measured the extraordinary winds, and photographed Triton's geysers. Then it kept going, out past Neptune, past the Kuiper Belt, into interstellar space. It is still transmitting, barely, a whisper from the edge of everything we know. And then there is Pluto. Pluto is no longer classified as a planet. Since 2006, it has been a dwarf planet, but it is still out there, still orbiting, still waiting in the cold. NASA's New Horizons spacecraft flew past Pluto on July 14, 2015, after a journey of 9.5 years. The images it sent back revealed a world far more complex and beautiful than anyone expected. Mountains of water ice rising 3,500 meters above a vast plain of frozen nitrogen, a heart-shaped feature on the surface that captured the world's imagination. glaciers of nitrogen ice flowing slowly across the landscape. A thin atmosphere of nitrogen, methane, and carbon monoxide that expands when Pluto is closest to the Sun and partially collapses when it moves away. On Pluto's surface, the temperature is -220 degrees Celsius. The Sun is a bright star. Its light takes over 5 hours to reach you. You would need a flashlight to see the landscape clearly. The gravity is 6% of Earth's. You weigh almost nothing. A gentle jump would send you meters into the air, and the silence is absolute. No wind, no sound, nothing but the faint hiss of your own life support, keeping you alive in the emptiest, coldest reaches of the solar system. Your suit handles the vacuum. It handles the radiation, which is minimal this far from the Sun. But the cold is extreme. After a few minutes, the thermal systems begin to lose the fight. The extreme cold makes the materials of your suit brittle. Flexibility decreases, a joint stiffens, a seal cracks. And when a breach occurs at -220 degrees Celsius, exposure is instantaneous. The end comes in seconds. Total survival time on Pluto, roughly 8 minutes. We have now visited every major world in the solar system: Mercury, Venus, Mars, Jupiter, Saturn, Uranus, Neptune, and the moons that orbit them, Europa with its hidden ocean, Titan with its methane rain, and Pluto, standing alone in the dark at the edge of everything. The verdict is unanimous. Every single world will end you, most of them in minutes. The fastest is Neptune at roughly 2 minutes. The slowest is Mars at roughly 10 hours, limited by your oxygen supply. Not one of these worlds is naturally habitable. Not one of them will welcome you with open arms. So how is humanity supposed to become a species that lives among the stars? The answer begins with the one planet we have already decided to visit, the one that gives us the most time, the one with the longest death clock, Mars. And it begins with a rocket that is bigger than anything ever built, a rocket that has been tested 11 times and has never reached orbit, a rocket whose creator just announced that Mars is no longer the priority. The plan, the setbacks, the future, that is where we go next. Chapter 8. The Mars Plan, Starship, Robots, and the Race to the Red Planet. Every world we have visited so far has tried to end us in minutes. Venus in 20, Mercury in 15, Jupiter in 3, Neptune in 2. Even Mars, the friendliest option, gives us roughly 10 hours before the oxygen runs out. And yet, despite all of that, despite every hostile atmosphere and every lethal radiation belt and every surface temperature that would melt steel or freeze nitrogen solid, humanity is planning to leave Earth. Not in theory, not as a thought experiment, as a project, with rockets, with timelines, with budgets, with engineers working right now in factories and laboratories and launch pads to make it happen. And the centerpiece of that plan is the largest rocket ever built. SpaceX Starship stands 122 meters tall when fully assembled on top of its super heavy booster that is taller than the Statue of Liberty, taller than the Saturn V rocket that carried astronauts to the moon during the Apollo program. The Super Heavy booster is powered by 33 Raptor engines in its latest configuration, generating roughly 74 meganewtons of thrust at liftoff. That is nearly twice the thrust of the Saturn V. The upper stage, the Starship itself, adds another 6 Raptor engines and is designed to carry up to 150 metric tons to low Earth orbit in its expendable configuration. In its reusable configuration, which is the entire point of the design, it carries less but can fly again. The reusable booster is what SpaceX calls the holy grail of rocketry. The Super Heavy booster launches, accelerates the Starship to roughly 8,650 kilometers per hour, detaches, flips around, and returns to the launch site where it is caught by the mechanical arms of the launch tower. SpaceX demonstrated this catch maneuver for the first time during Flight Test 5. The booster descended on columns of fire, and the tower arms closed around it like a giant pair of chopsticks plucking it from the sky. It was one of the most remarkable engineering demonstrations in the history of spaceflight. But Starship has a complicated record. As of late 2025, SpaceX had conducted 11 fully integrated Starship test flights. 6 were considered successful or mostly successful. 5 experienced significant failures, including explosions, loss of vehicle, and failure to achieve mission objectives. Starship has never fully reached orbit. Every test flight has followed a suborbital trajectory, ending in a controlled or semi-controlled splashdown. The vehicle is still in development. It is still being tested. It is not operational. And the Mars timeline has not gone according to plan. In September of 2024, SpaceX announced that it would launch the first uncrewed Starship missions to Mars during the 2026 transfer window. Earth and Mars align for efficient transfers roughly every 26 months. 5 Starships would launch, carrying Tesla Optimus robots to the Martian surface. The robots would begin preparing infrastructure, testing, landing procedures, scouting for water ice. If those missions succeeded, crewed flights would follow during the 2028 window. Then, in May of 2025, Elon Musk provided an updated presentation. He acknowledged the timeline was ambitious. He estimated a 50-50 chance of being ready for the 2026 window. The key bottleneck was orbital refueling. To reach Mars, a Starship needs to be refueled in Earth orbit by multiple tanker flights. Each Mars-bound Starship would require roughly 12 tanker launches to fill its tanks. 5 Starships going to Mars would require 60 tanker launches in a narrow window. And as of that date, SpaceX had never demonstrated orbital propellant transfer between 2 Starship vehicles. Then came February of 2026. Elon Musk announced that SpaceX would deprioritize Mars for roughly 5 to 7 years. The focus would shift to lunar missions. SpaceX holds a nearly $3 billion NASA contract to build the lunar lander for the Artemis program. The Moon, Musk acknowledged, would provide a quicker return on investment. A stepping stone, a proving ground for the technologies needed to eventually reach Mars. The 2026 Mars window will almost certainly pass unused. The 2028 window is now the earliest realistic target for an uncrewed landing attempt. Crewed missions to Mars, which Musk had once suggested could happen as early as 2029, are now unlikely before the early 2030s at the earliest. Expert consensus places a realistic first human landing on Mars somewhere around 2035 to 2040. The 26-month constraint is unforgiving. Earth and Mars align on their own schedule. If you miss a window, you wait 2 years. No exceptions, no shortcuts. The orbital mechanics do not care about your business plan or your funding cycle or your investor presentation. They care about gravity and geometry and nothing else. But the plan itself is sound. And when it eventually happens, whenever that is, here is what it will look like. Phase 1 is robots. Uncrewed Starships land on Mars carrying Tesla, Optimus, humanoid robots, and autonomous construction equipment. The robots deploy solar panels. They locate water ice deposits below the Martian surface. They begin setting up the infrastructure that humans will need when they arrive. Skeptics have pointed out that Optimus demonstrations to date have been partially remote-controlled, and that the robot's capabilities in an unstructured environment like the Martian surface are unproven. Fair criticism. But the concept of robotic site preparation before human arrival is not unique to SpaceX. NASA has been planning the same approach for decades. Phase 2 is cargo. 20 or more Starships launch during the next transfer window carrying 75 metric tons of payload each. Habitats, life support systems, power generation equipment, in situ resource utilization hardware. This last item is critical. ISRU, the ability to manufacture fuel and other resources from materials found on Mars. Without it, no return trip is possible. The plan calls for producing methane and liquid oxygen from Martian water ice and atmospheric carbon dioxide using a chemical process called the Sabatier reaction. Carbon dioxide plus hydrogen yields methane and water. The water is electrolyzed back into hydrogen and oxygen. The methane and oxygen become rocket propellant. You make your return ticket from the Martian air and Martian ice. Phase 3 is humans. The first crewed Starship arrives carrying a small crew. They enter habitats that the robots have prepared. They begin growing food in pressurized greenhouses. They conduct surface operations. They are the first human beings to stand on another planet. The habitats themselves are evolving. NASA ran the 3D printed habitat challenge, which produced designs like the Mars Ice House, a 4-story translucent igloo made from Martian water ice that doubles as radiation shielding. And in July of 2025, researchers at Harvard published a study in the journal Science demonstrating something remarkable. Bioplastic habitats made from polylactic acid, a plant-derived biodegradable material. Inside these structures, green algae survived under Mars-like conditions. The algae photosynthesized. They produced oxygen, a living, breathing habitat wall. A closed-loop system where the structure itself contributes to keeping its inhabitants alive. The habitat grows. The habitat repairs itself. The habitat breathes. Mars colonization is real. It is funded. It is being engineered. It is also behind schedule and extraordinarily difficult. The radiation problem has no complete solution. The gravity problem has no solution at all, short of spinning the habitat, which adds enormous complexity. The psychological challenges of permanent isolation millions of miles from Earth have never been tested at scale, and the first generation of Mars colonists will live in conditions more austere than any Antarctic research station. But the plan exists. The rockets are being built, the robots are being trained, and someday, possibly within the lifetimes of people listening to this right now, human feet will press into Martian dust. Now, let us return to a world we visited at the very beginning of our journey, the one that tried to end us in 20 minutes, the one with the most hostile surface in the solar system, because the most audacious colonization concept in history does not involve landing on that surface at all. It involves floating above it. We are going back to Venus, and this time we are staying. Chapter 9. Cloud Cities of Venus, living in Earth's evil twin. Earlier tonight, we stood on the surface of Venus and watched as the most advanced spacesuit ever built was dissolved, crushed, and cooked in 20 minutes. The temperature was 475 degrees Celsius. The pressure was 92 times Earth normal. The air was supercritical carbon dioxide laced with sulfuric acid. It was the most hostile surface environment in the solar system. And now we are going back. Not to the surface, 50 kilometers above it. At 50 kilometers altitude above the surface of Venus, something extraordinary happens. The temperature drops to between 30 and 50 degrees Celsius. That is roughly 86 to 122 degrees Fahrenheit. A warm day in many parts of Earth. The atmospheric pressure falls to approximately 1 bar. That is the same pressure you feel at sea level on Earth right now. The gravity is 90% of Earth's. Almost identical. You would barely notice the difference. In fact, at 50 kilometers above the surface of Venus, the conditions are more Earth-like than anywhere else in the solar system. More than Mars, more than the Moon, more than any moon of Jupiter or Saturn. The temperature, the pressure, and the gravity are all within the range of comfortable human habitation. There is only one problem. You are floating in the sky above a hellscape with no ground beneath you for 50 kilometers. Here is the elegant solution. Venus' atmosphere is almost entirely carbon dioxide. Carbon dioxide is a heavy molecule, a mixture of nitrogen and oxygen, The same mixture you are breathing right now is significantly lighter than carbon dioxide at the same pressure and temperature. This means that a container filled with breathable air would float in the atmosphere of Venus. It would be buoyant, naturally, without any special lifting gas, without hydrogen, without helium, just ordinary air. An airship on Venus does not need a separate gas bag and a separate crew compartment. The entire habitable volume is the lifting gas. You fill a large envelope with breathable air and it floats. The people live inside the thing that makes it fly. Every room, every corridor, every laboratory, every sleeping quarter contributes to the buoyancy that keeps the whole structure aloft. If you get a puncture, the air leaks out slowly because the pressure inside and outside is nearly equal. A small hole does not cause explosive decompression. It causes a slow, gentle leak that can be patched while the habitat continues to float. NASA studied this concept formally under the name HAVOC, High Altitude Venus Operational Concept. The reference design described an airship 129 meters long and 34 meters high, roughly the size of a football field. The outer skin would be protected from the sulfuric acid in the clouds by a thin layer of acid-resistant material. Solar panels on the upper surface would generate electricity. And there would be a lot of electricity to generate because Venus is closer to the Sun than Earth. The solar flux at Venus is roughly 1.9 times what Earth receives. Solar power on Venus is nearly twice as efficient as solar power on Earth simply because there is more sunlight. The travel time is another advantage that most people overlook. Venus is closer to Earth than Mars. At its closest approach, Venus is roughly 38 million kilometers away. Mars, at its closest, is roughly 55 million kilometers. And the alignment windows for Venus are more frequent. A mission to Venus could take less time and launch more often than a mission to Mars. There are challenges, of course, enormous ones. The sulfuric acid in the cloud layer is real. It is corrosive. Any structure floating in the clouds would need constant protection against acid degradation. Materials science for long-duration acid resistance is an active area of research, but it is not solved. There is no solid ground. Everything must float. Resupply, construction, maintenance, manufacturing, farming, all of it happens at altitude. If something falls, it falls 50 kilometers into a furnace. Dropping a tool on Venus is not an inconvenience. It is a permanent loss. And the wind. At the altitude of the proposed habitats, the winds blow at roughly 360 kilometers per hour. The entire atmosphere of Venus actually super-rotates. It circles the planet faster than the planet itself rotates. Venus rotates incredibly slowly. A single Venusian day lasts 243 Earth days. But the atmosphere at cloud level completes a full circuit of the planet in just 4 days. This means a floating habitat would circle Venus every 4 days, experiencing a sunrise and sunset roughly every 48 hours. A convenient, almost Earth-like day-night cycle created entirely by the wind. Now let us talk about what Venus was before it became what it is, because this matters for the colonization argument. Venus and Earth formed from the same cloud of gas and dust roughly 4.5 billion years ago. They are almost the same size, almost the same mass, almost the same density. Venus has been called Earth's twin, Earth's sister, Earth's mirror, and for a long time, possibly for billions of years, Venus may have actually been Earth's twin in the way that matters most. It may have had oceans. Evidence from Soviet and NASA missions detected granite-like rocks on the surface of Venus. On Earth, granite forms through processes that require liquid water. Climate models suggest that Venus could have maintained surface oceans for 2 to 3 billion years. 2 to 3 billion years of liquid water, of chemistry, of potential biology. Venus may have been a habitable world for longer than Mars ever was. And then the greenhouse effect ran away. Exactly how and when is still debated. Some models suggest it happened hundreds of millions of years ago. Others suggest it could have been as recent as 700 million years ago. But the result is clear. The oceans evaporated. The water vapor in the atmosphere trapped more heat. The heat released more carbon dioxide from the rocks. The carbon dioxide trapped more heat. A feedback loop, a spiral, a runaway process that turned a potentially living world into the hottest planet in the solar system. On Earth, most of our carbon is locked away in rocks. Limestone, shale, coal, petroleum. On Venus, all of that carbon is in the atmosphere as carbon dioxide. Both planets have roughly the same total amount of carbon. The difference is where it sits. On Earth, it is safely stored beneath our feet. On Venus, it is wrapped around the planet like a suffocating blanket. The parallel to our own situation is uncomfortable but scientifically grounded. We are releasing carbon from our rocks into our atmosphere. We are not on the path to becoming Venus. The physics are different. Earth's distance from the Sun and Earth's water cycle provide stabilizing feedbacks that Venus lost. But Venus demonstrates what happens when those feedbacks fail. It is a cautionary tale written in sulfuric acid and 475-degree heat. And then there is the question of life. Current life. Existing life. Right now. In the clouds. In 2025, a comprehensive review article published in a peer-reviewed journal examined all available evidence for potential biological activity in Venus' atmosphere. The findings were provocative. Ultraviolet absorption in the atmosphere resembles patterns produced by organic compounds. Chemical disequilibria exist in the cloud layer that are difficult to explain through known abiotic chemistry alone. Iron and magnesium sulfates have been detected, and the solar radiation at cloud altitude provides wavelengths and energy flux sufficient to support photosynthetic processes. The Committee on Space Research (COSPAR) assessed in 2023 that Venus clouds are orders of magnitude drier and more acidic than the survival limits of any known terrestrial organism. No life we know of could survive there. But the review acknowledged significant uncertainties in water content and pH measurements. And the possibility remains that life forms fundamentally different from anything on Earth could have adapted to conditions we consider impossible. If Venus once had life, and if that life had billions of years to evolve before the surface became hostile, it is conceivable that some organisms migrated upward, into the clouds, into the one zone that remained habitable, and adapted, evolved sulfuric acid-resistant membranes, developed metabolisms based on chemistry we have never encountered, became something entirely new. The Morningstar missions led by MIT planetary scientist Sara Seager aim to investigate exactly this. A probe descending through the atmosphere will search for complex organic molecules that could be associated with biological processes. It will not find definitive proof of life. That would require a more sophisticated follow-up mission, but it is the first step, the first taste of the Venusian clouds, the first direct sample of the most tantalizing atmospheric mystery in the solar system. Venus is Earth's evil twin, a world that shows us what our planet could become if we lose control of our atmosphere, a world with the most hostile surface imaginable, and a world that at 50 kilometers up, floating in clouds of acid above a furnace, offers the most Earth-like conditions in the entire solar system. Cloud cities on Venus are not science fiction. They are engineering problems, hard ones, possibly decades away from realization. But the physics works. The air floats, the sun shines. And somewhere in those golden clouds, something might already be alive. Now we travel outward again, past Mars, past Jupiter, back to Saturn, back to the moon with the orange sky and the methane rain. Because if Venus is the most surprising place to build a floating city, Titan is the most surprising place to build a colony on solid ground. A colony where you could walk outside without a pressure suit, where you could fly under your own power, and where the fuel to power a civilization lies in puddles on the surface. Titan is next. And this time, we are not just visiting, we are staying. Chapter 10, Titan Colony, the moon where humans could fly. Of all the worlds we have visited on this journey, Titan is the one that makes you want to stay. Not because it is comfortable, it is negative 180 degrees Celsius. Not because it is convenient, it is roughly 900 million miles from Earth. Travel time with current technology is 6 to 7 years. Communication delay is over 70 minutes one way. If you send a message to Earth from Titan, you will wait more than 2 hours for a reply. But Titan has something no other world in the outer solar system has. It has everything you need. Start with the atmosphere. Titan's atmosphere is primarily nitrogen, 98% nitrogen with traces of methane and hydrogen. It is dense, 1.5 times the surface pressure of Earth. This means you do not need a pressure suit. Let that settle in. On every other world we have visited tonight, a breach in your suit means rapid death. On Titan, a breach in your suit means you get cold, very cold. But you do not explosively decompress. You do not boil. You do not suffocate in seconds. You get cold. And cold is an engineering problem that humanity solved a long time ago. Insulated clothing, a heated inner layer, an oxygen mask. That is what a colonist on Titan would wear outside the habitat. No rigid helmet, no pressurized joints, no bulky life support backpack. You could move freely. You could work with your hands. You could bend and lift and carry with a freedom of motion that is impossible on any other world beyond Earth. Saturn's magnetosphere provides radiation shielding. The charged particles that make the surfaces of Europa and Mars so dangerous are deflected by Saturn's massive magnetic field before they reach Titan. And Titan's thick atmosphere provides an additional layer of protection. Cosmic rays that would pass through the thin atmosphere of Mars are absorbed and scattered by the dense blanket of nitrogen above your head. Radiation on Titan's surface is not a significant concern. In terms of radiation exposure, Titan is safer than Mars. Now consider the energy. Titan's surface and shallow subsurface are saturated with hydrocarbons. Methane and ethane in liquid form fill the lakes and seas. Solid organic compounds coat the surface like a layer of sediment. Kraken Mare alone, the largest methane sea, contains more hydrocarbon fuel than all of Earth's proven oil and natural gas reserves. And that is one sea on one moon. The total hydrocarbon resources on Titan are estimated at hundreds of times Earth's entire fossil fuel inventory. Burning hydrocarbons requires oxygen, and Titan's atmosphere has none. But water ice exists just beneath the surface, everywhere. Titan is an ice world. Its crust is water ice. And water is made of hydrogen and oxygen. Electrolysis, the process of splitting water into its component elements using electricity, would provide both breathable oxygen and hydrogen fuel. The electricity to power the electrolysis could come from burning methane with the oxygen you just produced, or from nuclear reactors, or from wind turbines spinning in Titan's thick atmosphere. And then there is the flying. Titan's gravity is 14% of Earth's, even less than the Moon, which is about 16.5%. On Titan, an 80-kilogram person weighs roughly 11 kilograms, a feather in human terms. And the atmosphere is dense, denser than Earth's. The combination of extremely low gravity and extremely dense atmosphere creates a flight envelope that exists nowhere else. On Earth, you cannot fly under your own power because your muscles cannot generate enough lift in our thin atmosphere against our strong gravity. But on Titan, the calculation changes completely. The lift required to become airborne is a fraction of what it would be on Earth, and the thick atmosphere provides far more resistance for wings to push against. The result is that a human being wearing lightweight wings could achieve powered flight on Titan using nothing but their own muscles. You could take a running start, flap your wings, and soar over methane lakes beneath a hazy orange sky. A Cessna light aircraft designed for Earth would fly perfectly well on Titan. Boats could sail on the methane seas. The tidal forces from Saturn's gravity create tidal changes of roughly 1 meter in Kraken Mare. Hydroelectric dams could harness this tidal energy. Wind turbines at high altitude could generate hundreds of megawatts. The energy possibilities on Titan are extraordinary. Habitats on Titan would take advantage of the available materials. The atmosphere provides nitrogen for breathing and for inflating habitat domes. Water ice provides oxygen and hydrogen. Hydrocarbons provide chemical feedstock for manufacturing plastics and other materials. A Titan colony could be largely self-sufficient in ways that a Mars colony could not, because Mars lacks the abundant chemical resources that Titan offers. The habitats themselves could be inflated domes of warm nitrogen and oxygen, double-walled for insulation, partially buried in ice to provide thermal mass and additional protection from the cold. The interiors would be warm, well-lit, pressurized to Earth normal. A colonist could step out of their habitat into the biting cold of Titan's surface, wearing insulated clothing and a respirator, do their work, and return to a warm, pressurized interior that feels remarkably like a building on Earth. There are challenges. Of course there are. The distance from Earth is the most obvious. 6 to 7 years of travel time means Titan colonists are on their own in a way that Mars colonists are not. Mars is months away, Titan is years away. Resupply missions would need to be planned half a decade in advance. Anything that breaks must be fixed locally. There is no calling for help. There is no emergency evacuation. If something goes catastrophically wrong, the colony survives or it does not. The gravity is a serious concern. 14% of Earth's gravity is low enough to cause severe, long-term physiological damage. Bone density loss, muscle atrophy, cardiovascular degeneration. The fluid redistribution effects that cause vision problems in microgravity would likely occur in Titan's low gravity as well. A permanent Titan colony would need centrifuges or rotating habitat sections to provide periods of higher gravity for its inhabitants. Sleeping in a slowly rotating drum that simulates Earth's gravity every night might be necessary to prevent the slow degradation that low gravity causes. The cold is relentless. -180 degrees is a constant engineering challenge. Every system must be insulated. Every mechanism must function at temperatures where most lubricants freeze solid. Metals become brittle, plastics crack. The materials science for Titan colonization would need to be advanced significantly beyond current capabilities. But Titan could serve a role beyond just colony. Titan could be a gateway, a refueling station for missions deeper into the outer solar system. Its abundant fuel resources and relatively low gravity make it an ideal hub for launching missions to Uranus, Neptune, and the Kuiper Belt. A ship could refuel at Titan using locally produced methane and oxygen and continue outward without carrying all its fuel from Earth. Titan becomes a truck stop on the highway to the stars. NASA's Dragonfly mission will provide the first detailed ground truth data about Titan's surface when it arrives. Dragonfly is a rotorcraft, a drone the size of a car that will fly through Titan's atmosphere, landing at multiple sites to analyze the composition of the surface and the chemistry of the atmosphere. It will study the prebiotic chemistry that produces those fascinating vesicle structures in the methane lakes. It will search for signs of chemical complexity that could indicate the potential for biology. Titan is a world where methane rain falls from golden clouds, where lakes of liquid hydrocarbons stretch to the horizon, where Saturn hangs in the sky like a pale ornament half hidden by haze, where a human could fly, and where the resources to power a civilization lie in puddles on the ground and in the ice beneath your feet. It is not a world we will colonize soon. The distance is too great, the technology too immature, the challenges too numerous. But of all the worlds we have visited tonight, Titan is the one that feels the most like possibility, like a place where humans could not just survive but thrive, build something, become something new. But there is one more destination before we talk about leaving Earth entirely. One more ocean to explore. One more world where the question is not how do we survive on the surface, but what is living beneath it. We are going back to Europa. Back to the moon of Jupiter. Back to the ocean hidden beneath the ice. And this time, we are going in. Chapter 11. Europa's Ocean. Diving into an alien sea. Earlier tonight, we stood on the surface of Europa for 15 minutes, and the radiation nearly ended us. Jupiter's magnetic field bathed us in charged particles that degraded our electronics and began destroying our cells within minutes. The surface of Europa is one of the most hostile environments we visited on this entire journey. But beneath the surface, everything changes. Europa's ice shell is roughly 29 kilometers thick. That is a formidable barrier, but ice is also a shield. As you descend through the ice, the radiation from Jupiter's belts drops dramatically. At just a few meters depth, the radiation is significantly reduced. By the time you reach the ocean, the ice above you provides more effective radiation shielding than Earth's atmosphere and magnetic field combined. The ocean beneath Europa is one of the most radiation-protected environments in the entire solar system. In 2025, researchers at the University of Leicester published a study exploring the theoretical feasibility of scuba diving in Europa's subsurface ocean. Not with current technology, not tomorrow, but as a thought experiment grounded in real physics, and the conclusion was fascinating. The ocean is potentially 60 to 150 kilometers deep. That is vastly deeper than any ocean on Earth. The Mariana Trench, the deepest point in Earth's oceans, reaches roughly 11 kilometers. Europa's ocean could be more than 10 times deeper. The pressure at depth in Europa's ocean would be extreme, but not unmanageable. Because Europa's gravity is only 13% of Earth's, the pressure increases much more slowly with depth than it does on Earth. At a depth of 100 kilometers in Europa's ocean, the pressure would be roughly equivalent to the pressure at 13 kilometers depth on Earth. That is deep. Deeper than any human has ever gone, but it is within the range of what engineered submersibles can withstand. Our deep-sea vessels on Earth routinely operate at 11 kilometers depth. A purpose-built submarine for Europa would not need to be radically different from what we already build. The temperature of Europa's ocean is a question with an uncertain answer. At the base of the ice shell, the water would be near its freezing point. But that freezing point is lower than 0 degrees Celsius because the water is salty. Salt depresses the freezing point. The ocean likely hovers around -2 to -4 degrees Celsius near the ice. But deeper, near the rocky seafloor, conditions could be very different. If hydrothermal vents exist on Europa's ocean floor, and many scientists believe they do, the water near those vents could be significantly warmer. On Earth, hydrothermal vents produce water at temperatures exceeding 300 degrees Celsius. The extreme pressure at depth keeps the water liquid. Around these vents, entire ecosystems thrive. Tube worms, giant clams, shrimp, microbial mats, all of it powered not by sunlight, but by chemical energy. By the reaction between hot mineral-laden water from the vents and the cold ocean around them. This process is called chemosynthesis. Instead of photosynthesis, where organisms use sunlight to convert carbon dioxide and water into energy, chemosynthetic organisms use chemical reactions. Hydrogen sulfide, methane, hydrogen gas. These chemicals react with oxygen or other electron acceptors, and the energy released drives the metabolism of microbial life. The microbes form the base of a food chain that supports larger and more complex organisms, all in total darkness. all without a single photon of sunlight. In 2025, a study published in Frontiers in Astronomy and Space Sciences examined the analogy between Europa's ocean and extreme environments on Earth. The researchers identified several terrestrial ecosystems that serve as models for what might exist on Europa. Deep-sea hydrothermal vents, subterranean ecosystems powered by radioactive decay in surrounding rocks. Deep-sea sediments, where microbial communities survive on vanishingly small amounts of chemical energy. In each case, the key insight is the same. Life does not need sunlight. Life needs energy and chemistry. And Europa has both. The energy sources on Europa are diverse. Tidal heating from Jupiter's gravity flexes Europa's interior, generating heat through friction. This heat may drive hydrothermal activity on the ocean floor. Radioactive elements in Europa's rocky core decay over time, releasing energy that can split water molecules through radiolysis. This produces hydrogen and oxygen ions that organisms could use as an energy source. And as we discussed earlier, the salt-rich surface ice may be slowly sinking through the ice shell, delivering oxidants and other chemicals from the irradiated surface to the ocean below. The question is not whether Europa has the ingredients for life. It almost certainly does. The question is whether those ingredients have come together in the right way over the right time period to produce biology. And the time period has been long. Europa's ocean may have existed for 4 billion years or more. On Earth, life appeared within the first billion years. Some evidence suggests it appeared within the first few 100 million years. If life arises whenever conditions permit, then 4 billion years is more than enough time. Europa Clipper will not find life directly. It will not dive through the ice. It will not sample the ocean. What it will do is characterize the habitability of the system from above. It will measure the thickness and structure of the ice shell. It will map the chemistry of the surface. It will detect and analyze any plumes venting from the ocean. It will measure the salinity and depth of the ocean using gravity measurements and radar. And it will tell us whether this ocean has the conditions necessary to support life as we understand it. If the answer is yes, and many scientists expect it will be, the next mission would be a lander, a spacecraft that touches down on Europa's surface, drills through the ice, and drops an instrument package into the ocean, or a mission that flies through a plume and captures droplets of ocean water as they are sprayed into space. Either way, the goal is direct contact with Europa's ocean, a taste of another world's sea. On Earth, there is an organism called Deinococcus radiodurans. It is sometimes called the world's toughest bacterium. In experiments conducted on the International Space Station, pellets of this microbe were exposed to the unprotected vacuum of space for 3 years. 3 years of cosmic radiation. 3 years of ultraviolet bombardment. 3 years of temperature extremes. And when the pellets were brought back inside, the outer layers of the microbial colony had died, forming a protective crust. But the inner layers were alive, viable, capable of reproduction. Life is tenacious. It persists in conditions we would have called impossible a century ago. If something similar exists in Europa's ocean, swimming in salt water, powered by the decay of radioactive elements in the rocks below, it would be the most important discovery in the history of science. It would mean that life is not a miracle, not a one-time accident, not something that happened once on one planet under one specific set of conditions. It would mean that life is a process, a natural consequence of chemistry given enough time and energy. It would mean the universe is probably full of it. That discovery would change everything, not just science, everything. How we see ourselves, how we understand our place in the cosmos, how we answer the oldest question our species has ever asked. Are we alone? We are not going to answer that question tonight, but we are closer to answering it than we have ever been. The spacecraft is on its way, the instruments are built, the ice is waiting, and beneath it, in the darkness, the ocean is there. It has been there for billions of years. whatever it holds, we will know within our lifetimes. But before we close this journey, there is one more possibility to explore. One more vision for the future of humanity among the stars. Not a planet, not a moon, not a natural world at all. What if we did not need to colonize hostile environments? What if instead of trying to survive on worlds that want to end us, we built our own worlds? From scratch, in the vacuum of space, designed from the ground up for human life. That is where we go next, and the ideas are older and stranger and more beautiful than you might expect. Chapter 12. Space Habitats, Building Earth from Scratch. In the summer of 1975, NASA brought together a group of scientists, engineers, and students at Stanford University for a 10-week study. Their task was to design a permanent home for humans in space. Not a space station, not a temporary outpost, a world, a place where people would be born, grow up, work, raise families, grow old, and never set foot on a planet. What they designed was the Stanford Torus. Picture a donut, a massive rotating donut 1.8 kilometers in diameter, 130 meters across the interior. The entire structure spins at approximately 1 revolution per minute. And as it spins, something remarkable happens. The rotation creates centrifugal force. On the inner surface of the donut ring, everything is pressed outward, toward the rim. And that outward force feels exactly like gravity. At 1 revolution per minute and a diameter of 1.8 kilometers, the centrifugal force on the inner surface is approximately equal to Earth's gravity. You could stand on the interior floor and feel perfectly normal. Drop a ball and it falls to the ground. Pour water and it flows downward. Walk and your footsteps have the same weight and rhythm as they do on Earth, except the ground curves upward on both sides of you. If you look straight ahead, the landscape rises gently, becoming steeper and steeper until it arches overhead and continues on the far side. You are standing inside a ring, and the entire ring is your world. The Stanford Torus was designed to house 10,000 people. The interior would contain residential areas, agricultural sections, parks, and recreational spaces. Sunlight would enter through a system of mirrors mounted at the hub of the torus. The mirrors would redirect sunlight into the interior, providing natural illumination for the plants and people inside. The agricultural ring would grow crops using intensive farming techniques. Fish farms and livestock areas would provide protein. Water would be recycled. Air would be recycled. Waste would be recycled. Everything would circulate in a closed loop, a tiny self-contained Earth spinning in the void. The total mass of the structure was estimated at 10 million metric tons. That is an enormous amount of material. Where would it come from? Not from Earth. Launching 10 million tons from Earth's surface would be prohibitively expensive. Even with the cheapest rockets imaginable, the material would come from space itself, from the moon, from asteroids. Lunar regolith contains aluminum, silicon, iron, titanium, and oxygen. Asteroid mining could provide nickel, cobalt, platinum, and water. The construction materials for the Stanford Torus would be harvested from the solar system and assembled in orbit. The Stanford Torus was never built. It was a study, an exercise in what was theoretically possible, but the concept was sound. The physics worked, the engineering was challenging but not impossible, and the idea did not die. It evolved. In 1976, a year after the Stanford study, a Princeton physicist named Gerard K. O'Neill published a book called The High Frontier. In it, he described a far more ambitious design, the O'Neill cylinder. Imagine 2 enormous tubes floating in space side by side. Each tube is 8 kilometers in diameter and 32 kilometers long. They rotate slowly in opposite directions, counter-rotating to cancel out gyroscopic effects that would otherwise make the structure difficult to orient. The interior surface of each cylinder is divided into 6 strips running the length of the tube. 3 of these strips are land, 3 are windows. The land strips and window strips alternate around the circumference of the cylinder. Sunlight enters through the windows and illuminates the land strips. The rotation provides Earth-normal gravity on the inner surface. Inside an O'Neill cylinder, you would see something that defies intuition. You stand on a flat surface. Green grass, trees, buildings, rivers. The landscape stretches ahead of you for 32 kilometers before curving up the walls of the cylinder and arching overhead. If you look up, you see more land, farms, forests, lakes. Hanging above you on the far side of the cylinder, lit by the sunlight streaming in through the alternating window strips. Clouds form naturally in the interior atmosphere. It rains, wind blows. The weather inside an O'Neill cylinder would be designed by engineers, but would eventually develop natural patterns and cycles as the ecosystem matures. O'Neill envisioned these cylinders as places where people would live full lives, not survival, not hardship, genuine communities with all the variety and richness of life on Earth. Skiing on engineered mountains, sailing on artificial lakes, climbing hills that curve overhead, and sports that exploit the unique geometry. A ball thrown inside a rotating cylinder would follow a curved trajectory that differs from anything on Earth. New games, new arts, new ways of moving through space that we cannot imagine until we experience them. Jeff Bezos, the founder of Blue Origin, described O'Neill colonies in a 2019 presentation as a superior alternative to colonizing planetary surfaces. His argument was straightforward. Planets have problems. Mars has the wrong gravity. Venus has the wrong atmosphere. Titan is too cold. Every planetary surface comes with constraints that human bodies were not designed for. But a space habitat can be engineered from the beginning with exactly the right gravity, the right atmosphere, the right temperature, the right light. You control everything. The population capacity of an O'Neill cylinder is enormous. A single cylinder with 32 kilometers of length and 8 kilometers of diameter provides over 300 square kilometers of habitable surface area. At reasonable population densities that could house millions of people, multiple cylinders could be built, dozens, hundreds. Bezos suggested that the solar system could eventually support trillions of humans living in O'Neill colonies without ever setting foot on a planet. The materials would come from asteroids. A single metallic asteroid like 16 Psyche, which NASA's Psyche spacecraft is currently heading toward to study, contains an estimated $10,000 quadrillion worth of iron, nickel, and gold. That number is meaningless by normal economic standards, but in terms of raw material, it represents enough metal to build millions of space habitats. The resources of the asteroid belt alone could support a civilization of a scale that dwarfs anything possible on the surface of any planet. There are practical concerns that go beyond engineering. Psychology is one of the most important. Living inside a finite enclosed structure, no matter how large, is fundamentally different from living on a planet with open horizons. Habitat designers have studied this problem. The solution involves multiple strategies. Areas of the habitat must be out of sight from each other. You should not be able to see the entire world from one vantage point. Vegetation should be allowed to grow semi-randomly rather than in perfectly manicured rows. Weather should be varied and partially unpredictable. Artificial day and night cycles with seasonal variation would prevent the monotony that comes from a perfectly controlled environment. The goal is to make the habitat feel natural, even though every aspect of it was designed. There is an even more ambitious concept called the McKendry cylinder. Instead of steel or aluminum, it would be constructed from carbon nanotubes, a material that is theoretically stronger than any metal we currently manufacture. A McKendry cylinder could have a radius of 460 kilometers. The interior surface area would be comparable to the entire land area of a country like India. A single structure containing an area large enough for hundreds of millions of people. Mountains, rivers, Oceans, weather systems, entire ecosystems, a world built from scratch and suspended in space. Space habitats have advantages that no planet can match. No hostile atmosphere, no toxic soil, no wrong gravity, no excessive radiation, unless you build too close to Jupiter. No 26-month transfer window, no 6-year travel time. A habitat at a Lagrange point, a gravitationally stable position where the gravity of two larger bodies balances out, requires minimal fuel to maintain its position. You could build habitats at the Lagrange points of the Earth-Sun system, the Earth-Moon system, the Jupiter-Sun system, anywhere the orbital mechanics provide stability. And habitats can be moved, not quickly. But a space habitat with an engine could slowly adjust its orbit, travel to a different part of the solar system, position itself near an asteroid for mining, move closer to the sun for more solar energy, move farther away if the population prefers cooler temperatures. A civilization built on space habitats is not rooted to any single location. It is mobile, flexible, adaptable. The Stanford Torus was designed in 1975. The O'Neill cylinder was proposed in 1976, nearly 50 years ago. We have not built either one. We have not even come close. The engineering challenges remain immense. The cost would be astronomical. The political will does not exist. Not yet. But the physics is real. The materials exist. The designs work on paper. And someday, perhaps not in our lifetime but in someone's lifetime, a structure will be built in space. A rotating ring or a spinning cylinder or something we have not yet imagined. A place where humans live and work and raise children and grow old and never once stand on the surface of a planet. Not because they cannot, because they chose not to, because they built something better. We are almost at the end of our journey, but there is one question we have not addressed, the biggest one, the one that underlies everything we have discussed tonight, every death scenario, every colonization plan, every habitat design, every robotic mission. Why? Why leave Earth at all? Why spend trillions of dollars and decades of effort to survive on worlds that are actively trying to end us? Why not stay home? The answer is in the next chapter, and it is not the answer you might expect. Chapter 13, The Case for Leaving, Why Earth Alone is Not Enough. 66 million years ago, an asteroid, roughly 12 kilometers wide, struck what is now the Yucatan Peninsula of Mexico. The impact released energy equivalent to roughly 10 billion Hiroshima-sized nuclear detonations. The resulting shockwave, heat pulse, and global firestorm extinguished approximately 75% of all species on Earth. The dinosaurs, which had dominated the planet for over 165 million years, were wiped out in a geological instant. They never saw it coming. They had no telescopes, no space programs, no ability to detect the threat or do anything about it. They were a successful species, thriving, diversified, adapted to nearly every environment on the planet. And then a rock from space ended their reign in an afternoon. We have telescopes, we have space programs, we have the ability to detect asteroids and potentially deflect them. NASA demonstrated this with the DART mission in 2022, which successfully altered the orbit of the asteroid moonlet Dimorphos. But our ability to detect every threat is incomplete. As of today, we have catalogued roughly 34,000 near-Earth asteroids, but new ones are discovered regularly, and the ones that are hardest to detect, the ones that approach from the direction of the sun, are precisely the ones we would have the least warning about. Asteroids are not the only existential threat. Supervolcanic eruptions have come close to ending human civilization before. The Toba eruption, roughly 74,000 years ago, may have reduced the global human population to as few as 10,000 individuals, a genetic bottleneck, a near-extinction event. And Toba was not even the largest eruption in Earth's history. The Siberian Traps eruption, 252 million years ago, drove the Permian-Triassic extinction event, the Great Dying. 96% of all marine species and 70% of terrestrial vertebrate species went extinct. The worst mass extinction in the history of complex life, caused by volcanic activity on our own planet. Gamma-ray bursts from distant stellar explosions could sterilize a hemisphere of Earth with virtually no warning. Global pandemics could devastate our interconnected civilization. Nuclear conflict remains a possibility that has not diminished since the Cold War, and our own industrial activity is altering the atmosphere and the oceans in ways that parallel the early stages of mass extinction events in the geological record. The theoretical physicist Stephen Hawking said in 2006 that humanity must begin colonizing other worlds to survive. His reasoning was not romantic, it was mathematical. If you have only one planet, and that planet is subject to random catastrophic events, then given enough time, the probability of an extinction-level event approaches certainty. The question is not whether it will happen, it is when. And if we are still a single-planet species when it happens, that is the end of everything we have ever built. Every piece of music, every work of art, every scientific discovery, every memory of every person who has ever lived. All of it gone. This is sometimes called the eggs in one basket argument. All of humanity's eggs, biological and cultural, sit on one planet. One asteroid, one supervolcano, one engineered pandemic, one sufficiently destructive war, and the basket breaks. Now let us talk about Venus. Not Venus the colony, Venus the warning. We discussed earlier that Venus was likely Earth-like for billions of years. Oceans, mild temperatures, potentially habitable conditions. And then, the greenhouse effect ran away. The oceans evaporated. The carbon dioxide accumulated in the atmosphere, and Venus became the hottest planet in the solar system. Here is the detail that should keep you awake. Venus and Earth have roughly the same total amount of carbon. On Earth, that carbon is locked in rocks, in coal, in petroleum, in deep-sea sediments, in the bodies of living things. Very little of it is in the atmosphere. On Venus, nearly all of it is in the atmosphere. The difference between a habitable world and a furnace is where the carbon sits. We are moving carbon from the rocks into the atmosphere. That is what burning fossil fuels does. We are taking carbon that was safely stored underground for millions of years and releasing it as carbon dioxide into the air. We are not going to turn Earth into Venus. The physics is different. Earth's distance from the Sun and our water cycle provide negative feedbacks that stabilize the climate. But the direction we are moving in is the same direction Venus traveled, toward a hotter atmosphere, toward higher carbon dioxide concentrations, toward a planet that is less hospitable than the one we inherited. Venus teaches us that planets are not permanent paradises. They are dynamic systems that can change. Tip: cross thresholds. Become something unrecognizable. Earth will not last forever as a habitable world, regardless of what we do. The sun is slowly getting brighter. In roughly 1 billion years, the increased solar output will begin evaporating Earth's oceans. In 3 to 4 billion years, the sun will expand into a red giant, and the inner solar system, including Earth, will be consumed. These timescales are enormous. They dwarf human civilization by a factor of millions, but they are real, and they mean that even in the absolute best-case scenario, even if we solve every problem we currently face, Earth has an expiration date. If humanity or its descendants want to persist beyond that date, they have to leave. There is another argument for leaving: not survival, expansion, growth, discovery. The resources available beyond Earth are virtually unlimited. A single metallic asteroid can contain more iron, nickel, and precious metals than humanity has mined in all of history. The water ice in the rings of Saturn alone could supply a civilization of billions. The energy output of the sun, if captured by a sufficiently large array of solar collectors, would exceed humanity's current energy consumption by a factor of billions. We are a species living on one grain of sand on an infinite beach, wondering if we should explore the rest. And then there is the knowledge argument. Every world we have visited tonight has taught us something about our own. Studying Venus teaches us about runaway greenhouse effects and atmospheric chemistry. Studying Mars teaches us about planetary habitability and what happens when a world loses its magnetic field. Studying Europa teaches us about the conditions necessary for life and the possibility that biology can arise in total darkness. Studying Titan teaches us about prebiotic chemistry and the formation of the molecules that life requires. Each hostile world is a laboratory. Each death scenario is a lesson. The solar system is a classroom, and we have barely walked through the door. The Fermi paradox looms over all of this. The physicist Enrico Fermi asked in 1950, if intelligent life is common in the universe, then where is everybody? The galaxy is billions of years old. It contains hundreds of billions of stars. If even a tiny fraction of those stars host civilizations, the galaxy should be teeming with evidence of their existence. Radio signals, megastructures, probes, something. And yet we see nothing. One possible answer to the Fermi paradox is that technological civilizations tend to destroy themselves before they become multi-planetary. They deplete their resources, they poison their atmospheres, they wage wars that end their species, they fail to develop the technology to leave their home world before a random cosmic event erases them. If this is the answer, then becoming multi-planetary is not just an ambition. It is a test, a filter that separates civilizations that persist from civilizations that vanish. We do not know if we will pass that test. We do not know if any species ever has, but we know that staying on one planet is not a strategy for long-term survival. It is a strategy for hoping that nothing goes wrong. And in a universe where asteroids fall and volcanoes erupt and stars brighten and atmospheres change, hope is not enough. Every planet in the solar system wants to end you. We have spent this entire documentary demonstrating that in vivid detail. But understanding how they end you is the first step towards surviving them. And surviving them is the first step towards something extraordinary. A species that is not bound to one world. A species that has spread its eggs across many baskets. A species that can lose a planet and still survive. Still remember, still create, still wonder. That is the case for leaving. Not because Earth is not enough. It is everything. It is the most beautiful, habitable world we have ever found. But because Earth is fragile, and so are we. And the only insurance against fragility is redundancy. More worlds, more habitats, more chances. We have one more chapter, one final accounting, a ranking of every world we visited tonight by how quickly it ends you and how soon we might colonize it. And then a question, the biggest question of all. What does the future of human civilization actually look like? Not in a century, not in a millennium, in the long run, the very long run. Where are we going? Chapter 14, The Planetary Scorecard and the Future of Human Civilization. We have traveled to every major world in the solar system. We have stood on surfaces that would melt us, crush us, freeze us, irradiate us, dissolve us, and blow us apart. We have descended into atmospheres where the pressure would collapse a submarine and floated above clouds of sulfuric acid. We have walked on ice, concealing alien oceans, and flown through skies of methane rain. Now let us see the final count. The fastest way to meet your end in the solar system is Neptune. 2 minutes, maybe less. 1,300 mile-per-hour winds in an atmosphere colder than negative 200 degrees Celsius. You are torn apart before the cold takes you. Next is Jupiter. 3 minutes. The combination of radiation, wind, pressure, and temperature creates a cascading system failure that no suit can withstand. Jupiter is not just hostile, it is overwhelming. Every danger in the solar system exists here simultaneously. Uranus gives you 3 to 5 minutes. The cold is the primary cause. The dense, frigid atmosphere conducts heat away from your suit faster than any thermal system can compensate. Saturn takes you in roughly 5 minutes. Similar mechanism to Uranus, but with even more violent winds. The storms on Saturn are among the most powerful in the solar system. Pluto grants you approximately 8 minutes. The extreme cold at -220 degrees makes your suit brittle. A seal fails. A joint cracks. Exposure is instant. Mercury and Europa are tied at roughly 15 minutes each. On Mercury, it is the radiation and the heat of the sun rising over the horizon. On Europa, it is Jupiter's radiation bombardment, degrading your electronics and your cells simultaneously. 2 worlds, same timeline. Completely different mechanisms. Venus gives you 20 minutes, the most hostile surface in the solar system. 475 degrees Celsius, 92 times Earth pressure, sulfuric acid in the atmosphere. Your suit fights valiantly and loses. Titan offers 2.5 hours. The cold is the enemy, -180 degrees, in a thick atmosphere that conducts heat away aggressively. But the pressure is manageable, the radiation is minimal. And for those 2.5 hours you are on the most habitable alien surface in the outer solar system. And Mars. Mars gives you the most time, roughly 10 hours before your oxygen supply is exhausted. Not because Mars is kind, because Mars is patient. It does not rush, it degrades you slowly. Radiation, dust, cold, low gravity, isolation. Mars plays the long game. That is the scorecard of survival. Every world wants to end you. The only differences are speed and method. Now let us talk about colonization, because survival and colonization are very different things. Surviving means lasting longer than a few minutes. Colonizing means building a permanent, self-sustaining human presence. And the ranking changes dramatically when you shift from how long can you survive to how soon could we actually live there. Tier 1 is Mars, the only world with active near-term colonization plans. SpaceX Starship, NASA partnerships, robotic precursor missions, 3D printed habitats, bioplastic greenhouse domes with living algae walls, in situ resource utilization for fuel and oxygen production. Mars is the first target because it is the closest realistic option, not the best option. The closest. The timeline has slipped. The challenges are enormous, but the engineering path exists and people are walking it. Tier 2 includes 3 candidates: Titan, Venus, cloud, habitats, and orbital space habitats near Earth. Titan offers the most abundant resources, the most Earth-like atmospheric pressure, natural radiation shielding, and the extraordinary possibility of human-powered flight. Its distances from Earth is the primary obstacle. 6 to 7 years of travel time, 70 minutes of communication delay. But the resources to power a civilization are sitting in puddles on the ground. Venus cloud habitats exploit the sweet spot at 50 kilometers altitude, where temperature, pressure, and gravity are all nearly identical to Earth. A balloon of breathable air floats naturally in the carbon dioxide atmosphere. The engineering challenges are significant, but the physics is elegant. And Venus is closer to Earth than Mars. Orbital space habitats, the Stanford Torus, the O'Neill cylinder, offer total control over every environmental parameter. Perfect gravity, perfect atmosphere, perfect temperature. The challenge is scale. Building a structure massing millions of tons in space requires asteroid mining capabilities we do not yet possess. But the advantage is that you are not fighting a hostile environment. You are building exactly what you want from scratch. Tier 3 is the long-term future. Europa subsurface colonies, Mercury lava tube settlements, O'Neill cylinders at massive scale, McKendry cylinders the size of nations. These are visions that require breakthrough technology, materials science we have not developed, energy systems we have not built. But they are not impossible. They are engineering problems on a very long timeline. And here is the cosmic perspective that ties all of this together. Astronomer Jill Tarter, who spent decades leading the search for extraterrestrial intelligence, has spoken about what she calls the cosmic perspective. The understanding that humanity is a small, fragile species on a small, fragile planet in a vast universe that does not care whether we survive. That perspective is not depressing, it is clarifying, because it tells us that our survival is our responsibility. Nobody is coming to save us. No benevolent civilization is going to appear and solve our problems. If we want to persist, we have to do the work ourselves. The search for life is accelerating. The James Webb Space Telescope is studying the atmospheres of exoplanets for biosignatures. Europa Clipper is heading for Jupiter's ocean moon. NASA's Dragonfly will explore Titan. The proposed Habitable Worlds Observatory, a next-generation space telescope, is designed to directly image and study roughly 25, potentially Earth-like exoplanets around nearby stars. We are building the tools to answer the question of whether life exists beyond Earth, and we may answer it within the next few decades. If we find life on Europa, on Titan, in the clouds of Venus, or on a world orbiting another star, it will transform our understanding of the universe and our place in it. It will mean that the process that produced us is not unique, that the chemistry of life is a natural consequence of physics given the right conditions and enough time, that the universe is not empty, it is alive. And if we do not find life, that answer is just as transformative, because it would mean that we might be the only ones. The only consciousness in a galaxy of 400 billion stars. The only species that has ever looked up and wondered. And that makes our survival not just important, but sacred. If we are rare, then our extinction would not just be a tragedy, it would be a cosmic loss. The universe losing its only way of knowing itself. Tonight we visited every major world in the solar system. We felt the crushing pressure of Venus, the radiation of Mercury, the patient hostility of Mars, the overwhelming fury of Jupiter, the hidden ocean of Europa, the methane rain of Titan, the impossible winds of Neptune, and the frozen silence of Pluto. Every one of them tried to end us, and every one of them taught us something. Venus taught us about atmospheres and runaway climate change. Mercury taught us about radiation and the price of proximity to a star. Mars taught us about the slow erosion of habitability and the importance of magnetic fields. Jupiter taught us about scale and power and the limits of human engineering. Europa taught us that life may not need sunlight. Titan taught us that chemistry can organize itself in ways we never expected. Neptune taught us that the universe does not slow down for human comfort. And Pluto taught us that even at the edge of everything, there is beauty worth finding. The solar system is our nursery. Every hostile world is a lesson. Every lethal surface is a classroom. And every colonization plan, however ambitious, however distant, however improbable, is an act of defiance against a universe that does not promise survival to anyone. Close your eyes and imagine this. A human being flying through the orange sky of Titan, with wings strapped to their arms, Saturn's rings arcing through the haze above them. Below them, a sea of methane, lapping against frozen shores. A submarine descending through the dark ocean of Europa, searchlights cutting through water that has never seen the sun. And in the beam of that light, something moving. Something that should not be there. Something alive. A city floating in the clouds of Venus. Sunlight streaming through translucent walls. Plants growing. Children playing. The acid clouds rolling beneath them like a golden sea. An O'Neill cylinder turning slowly in the void. Inside it, a landscape curving upward on all sides. Rivers and forests and mountains and a sky that is really a ceiling that is really more land. A world built from nothing. A home made from the raw materials of an asteroid and the stubborn insistence of a species that refuse to stay on one planet. These are not fantasies, they are engineering problems. Hard ones, decades away, some of them centuries away. But the physics works, the chemistry is there, the materials exist. And the species that split atoms and walked on the moon and built a telescope that sees the birth of galaxies 13 billion light-years away is not going to stop here. We will go, because that is what we do. We have always gone. From Africa to every continent, from shore to shore, from ground to sky, from sky to orbit, from orbit to the moon, and from the moon to everywhere else. Every planet in the solar system wants to end you, and every single one of them has underestimated us. If you enjoyed this journey through the solar system, please like this video and subscribe to the channel. Your support makes these deep investigations possible. Tell me in the comments, which world fascinated you the most? Which colonization plan do you think will happen first? And which planet would you visit if you could survive for just one day? These are not just questions for scientists, they are questions for all of us. Because the future of humanity among the stars is not someone else's story. It is ours, and it begins with the simple act of looking up and deciding to go. Thank you for watching. I will see you in the next investigation.